present, so they will present their videos, and then you will have a chance to ask them via Zoom. And then it will continue as an ordinary poster session. So authors of the posters, please make use of the space which is there, choose your stand and put there your posters. Furthermore, the poster session is supposed to be closed at 5 o'clock, and then we will have to move to public lecture, which is at the Faculty of Nuclear Sciences and Physical Engineering in Břehová ulice, which is, the map is in fact in this booklet, so you can find even instructions how to get there by tram number 22, and then either cross bridge by tram or on foot. It's quite easy for orientation because if you cross the bridge, there is a large square. On the left side, you will see our largest concert hall, Rudolfinum. And if you go further, you will miss Prague Conservatory, and then there is this Faculty of Nuclear Sciences and Physical Engineering. For tomorrow, on Wednesday, we had to change the time of the meeting of the International Advisory Board because of PCR tests, which will be held on Thursday. So on Wednesday, we will meet with the on-site members of the International Advisory Board or Committee of the Hypernuclear Conference, one floor up, in a meeting room which is called Earth, and which is just at the entrance of the restaurant where we used to have dinners, lunches, sorry. So on the right side there is a room of about 20 people where members will have lunch, and then there will be also Zoom connection with remote members of the International Advisory Board. So I ask members to be there tomorrow at 1:30. Then on Thursday, we arrange PCR tests for participants who need them. Unfortunately, the company SYNLAB was able to provide us with the tests on site here in the conference center, but only in the morning during the sessions. So we decided that we will go there, it's not far from here, it's about 300 meters. So we will go there beginning the lunch break. So we will meet with those 14 or 15 people at the registration desk, and one of members of the local organizing committee will take them there. And don't worry, you will not miss your lunches. We will arrange it that you will get lunches later once you get back. There will be for you. So that's all for these organizational messages, and now we will start the first session. I should ask, do we have the first speaker? Máme prvního řečníka? No? So the first online speaker is still not available, so PCR testing is PCR test. For Japanese, you don't have to have it. Only volunteers, don't worry. If you wish, you can join us, but you don't have to have it. So there will be change. We will have to change the program in the morning, and we will start with the second talk by, I ask Chairman Professor Stone to introduce the session and the first speaker.
Okay,
so thank you.
Thank you very much. I welcome everybody to this morning session. I hope you had an excellent welcome party yesterday and that you are all awake. So we will start with the talk by Tanida-san, and we will wait whether the first speaker appears on the net. Please, it's 20 minutes. Here is...
Is this a microphone?
No. This will control.
Yeah.
And
okay. This one is the microphone. Okay.
yes.
Thank you, and good morning, everyone. I would like to talk on the exotic hadrons as well. It's not the hypernuclei, but exotic hadrons at the Bell and Bell 2 experiments. Okay, so let me start from the E plus E minus collider for hadron spectroscopy. Well, the good thing is that, of course, it's an electron machine, so the background is small, especially for the E plus E minus to QQ bar production is flavor blind, and it's only, the cross section is only determined by charge square. So that's favorable to production of heavy hadrons, especially charm, well, compared to the experiment using a proton target or something like that, whereas the pion is abundantly produced with a cross-section of orders of magnitude higher than charm production. And another good thing is that missing mass spectroscopy is possible. Well, that's for fixed target experiments, that's a kind of matter, of course, but compared to the other collider experiments, such as LHC, this is a good advantage that the missing mass spectrum is possible. And you can measure, for example, absolute branching fraction, and you can also study decays with the missing particles, such as neutron, neutrino, and so on. And of course, the drawback is that the small production rate, but that can be compensated by high luminosity. And you know, many exotic hadrons and candidates are found and in the E plus E minus machines. And probably most of you remember the story of X3872. Yes, I know. Okay, so the hadron production in E plus E minus machines, electron machines, that the first one is the direct production. Direct production is mostly on the 1 minus minus states, such as psi, epsilon, and y. And initial state radiation allows that the lower mass than the original square root S. And also there is a two-photon processes where you can produce that the 0 plus plus states, 2 plus plus states, and so on. And of course, especially for baryons that produced by the indirect production method, it's a clock fragmentation from QQ bar or cascade decays, such as B meson decays into charm, and epsilon decays, and so on. Okay, here is a schematic view of the Bell experiment at the square root S around 10.6 GeV, and the integrated luminosity of around 1 at 1 inverse. And it's almost 4 pi detector with a good momentum resolution, electromagnetic calculator, PID, and circle-vortex detector. So it's a kind of a standard in the high-energy experiments, collider experiments. And actually, it's finished 10 years ago, and but still producing about, well, actually more than 20 papers every year. And now about more than half of these papers are on the hadron physics. So it's really a hadron physics machine nowadays. Okay, so before this talk, I picked up the list of recent results, but it made 3 pages. So I cannot talk all of them, apparently. Here's the list, and I don't have time to go through all of them. Second page, third page, and there's still more and more coming right now. So I cannot talk all of them. So you can take a look at these lists later, because the slide is available on the Indico page. So today, I will talk only on the 5 topics. The first one is on the baryons at the peak structure of the decay of lambda C to pk minus pi plus, and the spin parity measurement of Xi 2970, and the evidence for the new charm baryon in B decay. And the second part is the mesons, the search for the tetraclock XCC-SS bar, and then the other one is the exotic candidate in gamma gamma to a gamma psi 2s. And also, I would like to talk a little bit on the Bell 2 activities and the future prospects. Okay, so the first topic on the paper, baryons. Okay, so if you say the baryon, hadron spectroscopy in Bell, but most people may think it's on the quarkonim-like states, right? Well, that's true. That was true at least 10 years ago. But nowadays, we have more papers on baryons than mesons. If you take a look at the publication list, yes, that's true. We have more papers on baryons than mesons recently. Okay, the first topic is on the peak structure in the lambda C2 PK pi. I have shown this slide actually in the last hype 4 years ago. It's published in 2016. Okay, here's the Dalitz plot from the lambda C decay to PK minus pi plus. Of course, you can see several resonances which are well known, like lambda 1520, K star, and delta. But there's another line you can find in this plot here. So the question is, what is this? Okay, it's quite narrow. So actually, it doesn't fit with the norm one. So it may be a candidate of a new exotic hadron. I thought this. Then we tried to fit with that usual standard Bright-Wigner. Okay, here is the result. You can find the Bright-Wigner line something like this. And actually, it's not, the fit is not very good, especially in this region and also in this region. And the best chi-square DOF we obtained is at 308. So it's not so good. However, then we tried another fit to the flat function. And the flat function is this one. And it's almost you may think that it's almost a Bright-Wigner, but it considers the couplings to the lambda 8 channel. And the lambda 8 contribution is considered here. We also consider the interference with some other S-wave amplitude, which is presumably a tail from lambda 1405. And then we can reproduce the sudden drop of background. The background level is something like this, and then sudden drop here. That can be well reproduced. Then this fit improved the explanation for this structure, especially near this peak point. And the best chi-square over DOF is 257 over 243, and which is better than the Bright-Wigner fit by 7 sigma. So what this means? The answer is that the fit explains the peak as a threshold cusp. It's not the standard peak, but the threshold cusp with nearby lambda 1670 resonance. And that's the first identification of a threshold cusp from the spectrum shape. We several times say threshold cusps in many measurements, but we say that because the threshold cusp is expected, but it's not trivial. And we identify the threshold cusp from the spectrum shape. That's actually first. And another important thing is that the obtained lambda 1670 parameters are consistent with the one measured in the lambda C2 lambda eta pi decay, which is also published last year. And so like here, the mass is very good. For the width, we got some values, somewhat larger than the previous measurement, but it's still consistent within 2 sigma. Okay. And another important message from this measurement is that the other near-threshold exotic hadron candidates maybe they are not the standard Bright-Wigner peak, but maybe a cusp. That's especially true for for example, X3872. That may be a cusp, not a standard peak. Okay, the second topic is on the XIC2970. Actually, it's very clearly observed in the past measurement with a good statistic and signal-to-noise ratio. And the XIC2970 spin pi, we are going to measure spin pi t. And there is a wide variety of theoretical predictions on the nature of that state. And we try to identify the spin pi t in the decay mode, XIC2970 to XIC star 2645 pi mode, decay mode. Okay, for the spin, we determine the spin by the decay, this decay, cascade C to a cascade star, and the cascade C pi pi, and taking the angular correlation of those two pions. And if you take the angular correlation, the result is here. And it can be well fit with 1 plus 3 cosine square theta. That means this state has a spin 1/2. Okay? For the parity, we use the decay branching ratio to xi c star and xi c prime. This branching ratio is expected to be small for the negative parity because for the negative parity, this decay is in S wave, while this decay is in D wave. So this ratio must be very small. And for the positive parity, that is calculable based on the heavy quark symmetry. For the diquark spin is 0, then the R is order 1. While this is 1, then the R is as small as 0.2 or 0.3. And in the experiment, we got 1.67 with an error of 20-30%. Then that is consistent with the positive parity and the diquark or Brown-Bach, or strictly speaking, that's Brown-Bach spin over SL equals 0 only. So we got spin parity of 1/2 plus. What can we say from this? This is very interesting because this is the same as the infamous low power resonance, N1440, the first excited state of nucleon. And interestingly, the excitation energy is around 500 MeV, which is almost the same as that of the low power resonance. And actually, the low power resonance is well known, not foreknown. Okay, the difficult to explain low power in the quark model. That the single quark excitation, for the single quark excitation, first excited should be a negative parity state, like N star 1530. And it's surprisingly that this low power resonance is difficult, even in the lattice QCD. So that it's interesting because the present measurement may give a hint on the enigmatic structure of low power resonance. Okay, so the third topic is on the Newton baryon in B decay. Here's a search for the BZ decay to sigma C pi p bar. And we make the invariant mass spectrum for the sigma C pi. And here is a plot. And actually, we try to explain this peak structure with the known resonances, lambda C 2880 and 2940. But that's difficult to explain. And this fit is assuming a single new resonance. And this fit is favored by a 4.2 sigma with a mass of 2914 MeV, which is just in between those two, and plus minus 6 MeV, plus minus 4 MeV, and the width of about 50 MeV. And actually, the nature of this state is not known at all. So if you are interested in, please make some calculations to identify the nature of this state. Actually, in Bell 2 experiment, when we have much more statistics, actually we can study this spin, at least the spin, by the angular distribution of this decay. Okay. So now let me move on to the next mesons. For the mesons, we searched for the tetraquark XCCSS bar, inspired by the discovery of TCC state by LHCb. Actually, that we got nothing. That the spectrum can be explained by the sideband very well. In the 5 energies, epsilon 1s, 2s, 10.52, 58, but in none of these spectra, no significant peak. The upper limits are set like this. So that's unfortunate. Okay, the second thing is that the exotic candidates in the gamma gamma to gamma epsilon 2, psi 2s. Okay, and here is the invariant mass for the gamma psi 2s. And here we have two structures, a hint for two resonances. That's a candidate for exotics. The first one is around 3920 MeV. Maybe that may be a X3915 MeV found somewhere else. and maybe Chi-C2 state, but we don't know. For the second one, 1440, 4014, that's very near to the D star bar threshold. So again, it might be a cusp, might be a bound state, we don't know. Okay, so now let me turn to the third topic, the Bell2 activities and future prospects. And the Bell2 is the upgrade for the SuperKEK-B, and Bell to achieve that 30 times the higher peak luminosity with a nanobeam scheme. And actually, our goal is 50 times more statistics than the Bell experiment. Actually, the Bell2 is an ongoing experiment, and we are now taking data. Actually, until last week, this year. So far, we have accumulated about 428 femtobarn inverse, which is about 40% of the Bell experiment. And actually, the instantaneous luminosity already exceeded Bell by a factor 2. The new record is achieved 4.7 times 10 to 34. Yes, thank you. 10 to 34 on the June 22nd. That's just last week. And then the integrated luminosity will exceed Bell within a few years. I would say within few years. The goal is about 50 autobahn inverse around 2035, from 13 years from now. We are now here, 22 here, and we are now in the shutdown process here, and then we will achieve acquire 50 autobahn inverse in this year. Okay. Okay. For X3872, we rediscovered X3872 in this decay mode. That's the original decay mode we found, with 63 femtobarn inverse with a 4.6 sigma significance, with a 20% higher efficiency than Bell. And the near future, we will measure the absolute branching fraction with a 1 to 5 autobahn inverse using missing mass in B to XK. Second thing is that we took data on the energy scan around 10.75 GeV, because that in the recent publication, we found a structure at 10.75, which is a candidate for exotic state, exotic quaconime-like state. Then we took data at this energy, this energy, this energy, this energy, and compensating the previous energy scan of the Bell to establish the existence of the state or not. We took the data last year, half a year ago, and the analysis is still ongoing. Okay, here's the summary. Bell is still producing lots of interesting results. The observation of threshold cusp, spin parity measurement of a charmed baryon, and more. And more than 10 hadron spectral papers every year. And the Bell2, we acquire 50 times more statistics than Bell experiment. The instantaneous luminosity already surpassed the Bell experiment with a new record of 4.7, 10 to 34 is achieved. And we are doing analyzing the data. We got with a mini energy scan around 10.75 GeV. And we are expecting a lot of further discoveries. Thank you very much.
Thank you very much for your full of experiment and results. It was very interesting. Now we have questions which can be asked. Who would be the first person to ask questions?
I became curious when you said, that you didn't find peaks for, well, when you mentioned, that they were searching for CC and S-bar, S-bar.
CC S-bar, S-bar.
I was curious, to see your results, because I have a couple of papers with Lian Rondai in which we find that the DS, and D star S states, do not exist. So your findings are consistent with that. You don't find anything. Very good. Eh? So theoreticians, we already knew that before. Okay. Second thing, I mean, is I am curious. I mean, when you talk about this, I mean, peak, the lambda, the cusp, I mean, on lambda, lambda eta,
Lambda eta.
lambda eta. You know, I mean, I am curious. Is that
Excuse-
extra to the lambda 1670? I mean, a cusp. I mean, they are usual. I mean, in fact, you have such a good statistics there that you see a clear cusp.
Yeah.
And cusps normally come as a consequence of the interaction. But I mean, I'm wondering, the 1670 is very close by. You also mentioned it.
Yeah.
But you don't see it there. Why don't you see it there? You don't see it there in the spectrum, the lambda 1670. I mean, is there a reason why you don't see the lambda 1670?
Well, actually, in a sense, this is lambda 1670.
No, well, I mean, this is
Yeah,
lambda.
well, that's a,
But then
how you count.
if this is the lambda,
In a sense, this is the lambda 1670.
that is the lambda 1670. Okay, then because I mean, when you mentioned the next transparency, you say it is close to the lambda 1670. I was a little bit confused. If this is lambda 1670, fine, it's okay. I mean,
I'm not sure about the pole position, but if you fit with this function, this MF is still lambda 1674 MeV, which is about 10 or 12 MeV higher than this threshold, actually.
okay.
So apparently the peak position and this mass is different.
Okay, good.
If you calculate the pole position, it's again quite a lot different by order of 10 MeV.
Okay,
So-
next question. Perhaps you can discuss it
Yeah, okay,
over
thank
coffee.
you.
Next question. We still have time for a couple of questions over there.
All these exotic news or unknown new states, is there any hint of which character are these molecular states, or are these excited states internally, quark-excited states?
Which one?
I mean, there's always a discussion
There's always
About-
discussion, yes.
about molecular states or diquark quark configurations and all those things. Can you say from your data which type of model or understanding, better to say, is the confirmed or supported one?
Okay, for example, this one is a cusp, so that is usually associated with a virtual state. So in this case, it's a kind of molecular state. Well, it's exactly speaking, it's not molecular because it's not bound, but
So it's well, kind of a resonance.
yeah,
yes.
kind of molecular
Sure.
thing.
Okay, next question, the last one. If not, we will be carrying on, thanking the speaker again.
Thank you very much.
Now, the first speaker already connected, so we will now carrying on with the first talk by Mr. Guo, who will be talking about exotic hadrons with strangeness and charm. Is there a problem?
Can you hear me?
Yes. Yes, okay.
With strangeness charm. My talk will contain a few, I will discuss a few exotic states that include this open charm exotic mesons with strangeness and also some hidden charm states. Let me start with open charm mesons. Actually, these are really the new the mesons that started this new era of the studying of hadron spectroscopy. These are the D sub S 2317 and D sub S1 2460, which were observed by Barbar and Cleo almost 20 years ago. And these discoveries actually led to lots of studies because their masses are much lower than what one expected from quark model. For instance, here is the DS2317 mass, here's D sub S1 2460, and the black lines are those predicted by Godfrey-Isk model. And later on, there are many other mesons were observed, and one that really deserves to be mentioned contains both charm and strangeness is the so-called X2900, this structure. Of course, RCB in their paper, in their amplitude analysis, they dissolved this one to the reported different phases. One phase actually contains two Brown-Vignes for this structure, which they call X0 and X1 2900. That would be 0 plus 1 minus states. Of course, I think this is not really settled yet whether this what the fine structure of this peak is. For the hidden charm sector, in fact, most of these new states beyond the expectation from quark model, they are in the hidden charm sector. And this includes the very famous X372, they also as known as Cassio-1 3872, this is talked about by the last speaker. And then this discovery was followed by the discovery of many other new structures. And only until 2 years ago, states with hidden charm and strangeness were reported first by BESS3. They reported this ZCS 985 in DS D star invariant mass distribution. This is also close to DS D star threshold. And then RCB, they reported the so-called ZCS 4000 and ZCS 4220 later on in DeepSci in DeepSci-K invariant mass distribution in BDKs. You see, these structures, they are in the hidden charm mass region, in charmonium mass region, but they contain explicit strange quantum numbers. So this, if they correspond to really hadrons, they must be exotic hadrons. Here, these are the distributions observed by BESS3 and RCB. See here, BESS3, they saw this structure in different energies of E plus and minus collisions. The clearest signal was seen in the at the energy of 4.681 GeV of E plus minus system. So there is a near threshold enhancement, and for other energies the enhancement is not very clear. But this one there is a clear enhancement. And RCB, you see, that's their observations. So here is what they call 4000. You see, this 4000, this structure is much broader than what BESS3 observed in the D star final state. The other one is 4020, is around this peak. However, we can notice that this 4000 is around DSD star threshold, but the 4020 is higher than the threshold by 100 MeV. On the other hand, there is a deep just before this peak, and the deep position is around D star, DS star threshold. And RCB, in their analysis, they reported favored quantum numbers to be 1+. And also BESS3, they use 1+ assumption, and the description to the data is good. Some other exotic hadrons with strangeness and charm are the P sub CS states, which are the hidden charm pentaquarks with strangeness. I think everybody knows that the hidden charm pentaquarks were first observed by RCB in the 2015 analysis of lambda B decays into deep side proton Keon in deep side proton final state. And later on, a few years later, in their analysis of the round 2 data with statistics with data samples 1 order of magnitude higher, they saw these fine structures of what they reported before. This basically contains 3 narrow structures. They corresponds to PC 4312, PC 4440, and PC 4457. And in last year, they reported their first evidence for the existence of hidden charm pentaquarks with strangeness. This time, this was reported in the decay of chi B into deep side lambda and Keon. So this is the deep side lambda in very mass distribution. You see here there is a little peak here, and this peak could be described by one resonance. Of course, there is also a possibility that this is due to 2 resonances with very nearby masses. So this is their fit with introducing 2 PCs, and this is with 1 PCS state. So let me go to the theory part. Just after the discovery of D sub S 2317 and D sub S 1 2460, there were already lattice calculations. Of course, there are many other theory or model calculations as well. But the lattice calculations at that time, they used the operator used in their calculation contains only quark-antiquark type. This means they construct operators of the type of CS bar, and then they compute the mass spectrum. What they found is that the mass that's obtained in such kind of calculations is much higher than the mass observed by experiments. So this was obtained by several different lattice QCD collaborations. And this higher mass is close to the prediction from quark model. And about 10 years later, Daniel Muller and his collaborators, they reported the first calculation by including both quark-anti-quark type operator and DQ bar type operators. So with this kind of more complicated operators, they can obtain mass which is consistent with what observed by experiments. So basically, they computed the difference between the mass and the spin average of the ground state charm strange mass on mass, and this is their calculated value, which is consistent with the experimental value. And this calculation was done with pi mass of 156 MeV. And a few years later, the Regensburg QCD collaboration, they also did another calculation for this charm strange mass on spectrum. And their calculation used a pi mass of around 150 MeV. So this is really close to the physical pi mass. And you see here the obtained ground state charm strange mass on masses, the pseudoscalar and the vector CS bar mass on masses, they are really close to experimental data. And this 0 plus, that's would corresponds to D sub S 0 star 2317, is also close to the observed value, although still 30 MeV higher. And the 1 plus mass on mass is also close to the observed value. So this just tells us the dk or d star k for the 1 plus case. This type of mass on mass on components would be very important in understanding their nature. And of course, before these lattice calculations, there were already other theory studies considering this dk and d star k interactions. The reason why we can do that, that's because these 0+ and 1+ mesons, they can couple in S-wave to the system of ground state charm mesons and light pseudo-scalar mesons. And these pion-kaons, they are the pseudo Gaussian bosons of chiral symmetry breaking. And then we can construct chiral effective theory for the low energy interaction of this system. And because of the existence of this 0+, 1+ residences near the DK, for instance, the threshold, and then one is to include some non-perturbative treatment of this interaction, and then we can just use Lippmann-Schwinger equation to resum all these interactions, just as done in serious papers of this development of unitized chiral Bayesian theory. And what we have done this about 10 years ago is that we constructed the chiral Lagrangian for the scattering between the ground state charm mesons and light pseudo-scalar mesons up to the next leading order in the chiral expansion. And then this contains 6 low energy constants. And one can see one of them actually can be fixed from experimental data of the ground state charm meson mass splitting, and the others we need to fix from lattice data. So we fix these parameters by fitting to lattice calculation of the scattering lengths of a few channels of the charm meson, light meson scattering. These channels are free of the quark anti-quark annihilation diagrams, so they were relatively easy to be computed on lattice. So in this way, we fix all the parameters, and then we can make predictions on this the masses of charm strange mesons. So you see, this is a prediction of the 0+ DS0 star meson mass. One should see that this channel is not included in the fitting. So this is a prediction of the fitting of that theory. So you see the center, the central value of the prediction really agree very well with the observed value of the S0 star mass, and one can also use heavy quark spin symmetry to relate the 1+ sector to the 0+ sector to give prediction on the mass of DS1 meson. So the DS1 meson predicted mass is also very close to the observed value. And one can further use heavy quark flavor symmetry, because the interaction between charm meson and light mesons would be very similar to the interaction between a bottom meson and light meson. So one can predict 0+ and 1+ B bottom strange meson masses. So these are the predictions. These states so far have not been observed. One difficulty in observing them would be these states, the final states of the decay modes of these two mesons always involve photons, so the soft photons. And one can compare these predictions with, however, lattice predictions in this paper. So the lattice predictions agree very well with this prediction from unitized chiral approach. And in this theory description, one can also extract the probability of the calculated DS0 star meson and DS1 meson as dk and d star k hadronic molecules. So the probability of this DS0 star to be a dk bound state is around 0.7, is around 70%. Here I list several different iterations from direct or indirect lattice QCD calculations, so by different groups. As all of them have 0.7 or even larger probability for the DS0 star to be a dk hadronic molecule. So as So far, I have talked about these open charm mesons. This dynamics is very special because of the special rule of the kaons. The kaon, on the one hand, the kaons are light enough, so we can approximately study their dynamics, their interaction with other hadrons using chiral dynamics. And on the other hand, they are heavy enough because the leading order chiral dynamics gives us the so-called Wernberger-Tomaszeva term, which is proportional to the energy in the near threshold region to the Gaussian boson, to the kaon. So the kaon mass is much heavier than the pion mass. So the interaction strength is also much stronger than the interaction between pion and the matter field. So this leads to the rich non-perturbative phenomena involving strange quark, leads to some near threshold states. And the Wernberger-Tomaszeva term actually is very universal. So because this is just controlled by chiral symmetry, so we can expect that the sim interaction should also play a role in the system of kaon and some other matter field. For instance, some other heavy mesons. Here I just put D1, D2, and B1, B2. And then one can also make prediction on, one would also expect the existence of bounces in such systems. For instance, there was a consequence of this interaction to be a 1 minus, the existence of 1 minus charm string meson with a mass around 2.87 GeV. Actually, this is very close to the DSJ star 2860. And in this scenario, the key pattern of the DS1 star 2860 can also be naturally understood. And we can even expect this to lead to rich spectrum of doubly charm baryons with the straightness. But for this system, the spectrum is richer because of the existence of P-wave excitation within the two charm quarks. So the two charm quarks, they can have a P-wave excitation. And from quark model calculation, it is known that the P-wave excitation energy of the charm diquark is around 200 MeV. So this means if we study the interaction between kaon and cascade CC, the double charm baryons, then one has to include the existence of a P-wave excited cascade CC state, which has a mass lower, omega CC state, which has a mass lower than cascade CC and kaon threshold. And here is a spectrum that one would expect by coupling all this cascade CC K bar system and the omega CC P-wave excitation. So one would expect a pair of states below 4.2 GeV. And the x-axis labels the strength of this P-wave state coupling to the cascade CC and kaon pair.
There is just 1 minute to left. There is just 1 minute to.
Oh, 1 minute. Oh, sorry. So then I need to quickly go through. So basically, we have all this many states. They are in the different multiplays, and we expect that this D key bar from vertical states, actually this was also seen in lattice calculation. And because K bar is just a Gaussian boson, and when we expect K star interacts more strongly with other state, and then it's natural to expect some D star, K star bar bound state. This would correspond to X 2900. And then one would expect this also exists, has some spin and bottom partners. And I go very quickly the hidden charm sector. So basically the ZCS structure, this can be understood as SU3 partner of the ZC3900. And at the same time, a triangle singularity plays an important role to enhance the structure at the energy 4.681 GeV, as you see here. And I skip this page. And actually, the RCB observed structure can be fitted simultaneously with the best 3 data by assuming the same 2 ZCS states corresponding to ZCS 3985, and the other one would be 4110. It's around the deep, it's not around this peak. And yeah, this just shows that both ZCS and ZC they can be described simultaneously, assuming them to be SU3 partners. And at last, this is the last page before the summary. So this, we also expect the existence of many hidden charm pentaquarks. Here I show the hidden charm pentaquarks with straightness, PCS, prediction using very simple model, considering vector meson exchange. And you see, so far there are only evidence for these 2 guys, but Venn actually expects there exist many more states with hidden charm and straightness. So this is summary. Because of time is already out, so I will not repeat. Thanks.
Thank you very much for your very nice talk. Now the talk is open to discussion, questions. Here.
Hi, Feng Kung. Good review.
Hi, I love you.
Good review for such a short time. Let me make one precision. I mean, you mentioned there the compositeness of the DS2370, the DS0, and you mentioned there around 60–70%. Exactly, right. This is correct, and this is what the calculations say, and lattice and all that. But this is only the D, you know, of course, but that's the DK component. On top of that, I mean, there's the DS eta. And the DS eta also have, I mean, a certain, I mean, about 30%, I mean, also, I mean, probability. So that the sum of the 2, the DK and the DS eta, amounts to about 100%. So, I mean, we can say if you count the 2 components, this is essentially, I mean, a 100% molecular state. Just a precision to know that this probability is only for the DK component, but you still have the other one.
Thank you, Aloysius, for this comment. Yes, this probability is only for DK, and for D sub S eta, for the D sub S eta, because the threshold is much higher, and the reliability of using this one-man set as the description of the probability of the D sub S eta component inside D sub S 0 star 2317 is not that precise. So the uncertainty is much larger. But I agree that this is only for DK, and there are other components. And one origin comes from the DS eta. Actually, in this unitized chiral description, only DK and DS eta are included. Yes, thanks.
Next question. We still have time for one question. No, if not, let us thank the speaker again.
Thank you. I really hope I was there.
And the next speaker is Isaac Vidania, who will tell us about hyperons and neutron stars. 25, yes.
Okay, so thanks First of all, I would like to thank the organizers for the invitation. This is not the last version, sorry. I just unloaded this morning the last one. So if you go to the site. Okay, then let me take profit to thank the organizers and the Horizon 2020 program for supporting us. And I want to say that it's really a pleasure to be in Prague. This is the sixth time in my life being in Prague, and it's really nice to see people in person and not through a screen. So this has been a very strange time for all of us. 1.5 years, and hopefully we will be back at home.
We have to reset the timing as well.
Okay, so in this, the next 20 minutes more or less, I'm going to review more or less what is the role of hyperons in neutron stars, focusing mainly on the role of the equation of state and the famous hyperon puzzle, and I will review some of the solutions that people have proposed. And then if I have time, I will try to show you that they have also influence in other quantities like transport properties. So let me start with just summarizing some well-known properties and well-known recent observables from neutron stars. So a neutron star is nothing else but one of the possible types of stellar compact remanence that result from the gravitational collapse of a massive star. And here massive means something between 8 and 25 solar masses. Above 25 solar masses, what you will get in the end is a black hole. And these are formed during a supernova type 2 1b or 1c event. So the masses are, we know, in the range 1 to 2, and we are now sure that there are at least 3 objects with 2 solar masses. The radius typically between 10, 12 kilometers, maybe a bit more or less, which means that the average density of these objects is extremely high, something from on the order of 10 to the 14 to 10 to the 15 grams per cubic centimeter. If you just count the baryons that are in the interior, the number that you get is of the order of 10 to the 56 or 57. So from a nuclear physics point of view, these are giant nuclei, or giant hypernuclei if you want. And they also present extreme magnetic fields at the surface, which means that in the interior they can be even larger. So for millisecond pulsars, at the surface, the magnetic fields are in the range 10 to the 8, 10 to the 9 Gauss. For the so-called normal pulsars, which are pulsars rotating with periods of 1 second, this is already of some order of magnitude larger, 10 to 12. And there are very extreme, highly magnetized objects, these so-called magnetars, where the surface magnetic fields can be even in the order 10 to 14 to 10 to the 15 grams. Also, the electric fields are huge, so something of the order of 10 to 18 volts per centimeter. The temperature is important in the first stage of the evolution of the object, and they range from 10 to 6 to 10 to 11 kelvins. And if you look into the distribution of the periods of these guys for more than 1,500 pulsars, the majority of them has periods of the order of 1 second, and these are the so-called normal pulsars, but there is a second family of about 200 guys that are rotating at about periods of the order of milliseconds, and these are the family of the millisecond pulsars. So, recent observables. So as you know, in the last decade, we have been very lucky because at least 3 objects have been detected with 2 solar masses. And they have been observed thanks to the measurement of the so-called post-Keplerian orbital parameters. So these are orbital parameters that are purely relativistic, so they don't appear in non-relativistic systems. In particular, one of these parameters is the Shapiro delay, where, well, there are 2 Shapiro delays, 2 components. There is a shape and a range. And basically, these quantities that are observed contain information on the masses of the two objects and the inclination of the orbit. Anyway, if you look into these three guys that were observed in the last decade, the first thing you immediately notice is that they are very similar. So they are formed by a compact objects with two solar masses rotating at millisecond pulsars in an orbit with, where the companion is a white dwarf. And the orbit is very circular, so it has a very low eccentricity. So this is not a casualty. So it means that probably these three guys has been formed in a very similar scenario. So you start basically with binary system, which is made with two ordinary stars, one massive and one not so massive. The more massive ones evolve. At some point, it explodes in a supernova, forms a neutron star. The explosion is violent, but not so much, so the system remains bound. And then you have a compact object orbiting with an ordinary star that is continuing his evolution. And since it's not very massive, it will spend a lot of time in the main sequence. And this is crucial, because he has a lot of time to transfer matter to the compact star. And therefore, the mass increases. So the original pulsar can be formed with masses lower than two solar masses, but because of the accretion from the companion is increasing, because there is a lot of time for do that. And at the same time, it's also transferring angular momenta, so it's spinning faster. So in the end, you have a compact object, which is very massive, is spinning very fast, and the companion, which is not very massive, will end his life as a white dwarf, which is basically essentially what you have in these three systems. Then, of course, the other quantity that is highly desired is the measurement of the neutron star radii. But the radii are very difficult to measure. And the reason are very simple. They are very small objects, so it's about 10 kilometers, and they are very far from us. And in fact, just to give you an idea, I corrected this number yesterday thanks to Laura, because I thought it was 400 light years. It was, but the point is that this guy is moving. And now, so this is the closest neutron star that you have now, and it's about 200 light years from us, and it's moving, no, it's not static, so it's a runaway star moving at 100 kilometers per second. So one possibility to detect, and this was the first type of measurement for the radii, is to use the thermal emission from X-ray, from the so-called low mass X-ray binaries, which are these kind of systems that I mentioned before, where you have a white dwarf and the compact object. And in this case, what you have to do, you have to measure the flux of X-rays. You have to make some estimations or modeling for the surface temperature, which is complicated because you have to assume some black body spectra on models for the atmosphere. And the more tricky part is that you have to estimate the distance to these systems, and this is not easy at all. And then you have also to correct everything for the gravitational redshift. So when you all do that, in the end of the day, you can extract a relation that gives you the star of the radius of the star in terms, okay, in an implicit way together with the mass. So this is, say, like more classical way. And in fact, there were already some estimations. These are two works that we analyzed the same five quiescence low mass X-ray binaries, but the results on these two works were a bit controversial because one of these papers were basically giving values more classical on the range of 12 kilometers, whereas this paper by Guillot and company, they were predicting very compact objects. Anyway, thanks to the nicer vision, we have now a new way of measuring the radius. And in this way, in this case, what you do, basically what they do, is they track the X-ray emission from the hot spots. So basically you have a neutron star where there is some hot spots where there are more heat. And then the idea is to model the pulse profile, which depends on the mass-radius relation. And this has been done, at least for these two sources. This guy is one of these two solar mass objects. And, well, the two, I will show later a plot where you can see the results, but unfortunately the error bars are still quite large. And then we are happy now because we are living in a new astrophysical area, which is the area of the gravitational wave. And as you know, almost 5 years ago, there was a detection of the first gravitational wave signal coming from the merger of two neutron stars. So this was detected by the LIGO collaboration. So this is the gravitational wave signal before the merger, so it's the in-spiral epoch. And then after that, there was also the detection in the electromagnetic spectra, first of gamma rays and X-rays, and then in the next hours and days, there were observations in other parts of the spectra. So from this observation, it's in principle possible to put constraints on the mass that are derived from the so-called shear mass, and also on the radius derived from the so-called tidal deformability. So if you put everything together on a mass versus radius plot, this is a kind of summary of our present knowledge from astrophysical constraints. So all these bands here, these are constraints coming from this gravitational wave event. The nicer result for these two objects are these blue bands. So these are for this guy for which we know with high precision the mass, and then this other band here correspond to this other source. And then, okay, there is an addition, this Bayer language correspond, this is another result coming in this case from the Rossi X-ray timing explorer. So as you see, the situation has improved, but still there are too much large error bars, especially in the radius. So we cannot yet distinguish or choose one of the question of state, because in principle some of them are still valid. So that was I wanted to mention from this introduction, and then let me move to the hyperons. As you know, hyperons are expected to appear in the core of a neutron star at densities in the range 2 to 3 times saturation density, and the reason is simply that at such densities, the chemical potential of the neutrons is so large, of the nucleons in general, let's say, such that the conversion of nucleons into hyperons is simply energetically favorable. But the problem is that hyperons are fermions, and this is something general that happens to other fermions. As soon as you create a new fermionic species, there is a release of the Fermi pressure in the system. And this means that the question of state is softer. It's soft simply because you are creating a new Fermi sea. And this, as a consequence, has that the mass, and in particular the maximum value, is reduced, and is reduced in most of the models to values much smaller than the observation. And this is a problem, because we know that at least 3 objects have 2 solar masses, which means that any model that you want to describe the question of state of dense matter should at least predict maximum masses larger than 2 solar masses. And this is a problem. And of course, the natural question that suddenly arises is that, well, can hyperons still be present in the interior of a neutron star under the view of this stringent constraint? So this is the hyperon puzzle, and the solution to this puzzle essentially requires a mechanism or some mechanisms that essentially will provide additional pressure or repulsion at high densities in order to make the question of state stiffer enough such that the maximum mass is compatible with observation. And there are different ways to do that, and people have considered different possibilities. The first one is simply coming from the fact that, well, we don't have a complete knowledge of the hyperon nucleon and hyperon interaction, so maybe there is still some room left for the two-body part. So one of the solutions has been explored mainly on the context of relativistic mean field models, essentially consists in the introduction of vector mesons, in particular the Hayden-Strange phi meson, in order to provide this additional repulsion at high densities. Now there is a very promising result coming from the use of chiral hyperon nucleon and hyperon potential from chiral effective field theory, and I will show you some preliminary results from the Bonn-Munich group where they show that the larger single particle potential already at the two-body level is more repulsive than what you obtain typically if you use some more traditional meson exchange models. And then, of course, there is the question of three-body forces. Well, three-body forces, you know, from traditional nuclear physics are important, so probably they play a role also in the hyperonic sector. And then there are more exotic solutions that, okay, some people say, well, what happens is that before you have hyperons, you simply deconfine to quark matter, and that's the end of the problem. So let me analyze a bit the different solutions. Let me start with this solution that has been used basically on the relativistic mean field models. And this is, well, the idea is very simple. So you know from the nuclear-nuclear interaction or the baryon interaction is that the exchange of vector mesons is generating repulsion at short distances. So the idea is to add, as I mentioned, some vector mesons that in principle couple only to hyperons, in particular the phi mesons, in order to get this additional repulsion at short distances or high densities, if you prefer. So if you go to the literature, to the archive, and you type repulsion, hyperon, blah, 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 you will find thousands of papers. So there have been an enormous cornucopia of papers based on these models. So I will not summarize them because basically it's impossible. So let me just show you some 5 representative calculations from the 5 different groups. Anyway, the message is that basically all of them are compatible with observation because, okay, in the end of the day, there are some free parameters that are adjusted ad hoc in order to get 2 solar masses. You can believe or not, I personally don't, but this is just my personal opinion. So then we go to this second solution that is very promising from chiral perturbation or potential derived from chiral effective field theory. And in fact, this plot was already shown by Angels. This is the result from a Bruckner-Hartree calculation, I think with the continued choice made by the Bohn-Jülich Munich group, where this is the single particle potential of the lambda at 0 momenta as a function of the density. The red bands are the results with just two body forces, and then the blue ones contain also the contribution from 3 body ones. But just for the moment, just look when you compare this result with the one they obtained using more traditional measurement change potential, like the Jülich, in this case the 0.4, and one of the 9 meg in 97. This result with this chiral potential gives more repulsion. So this is very promising and is going in the good direction. The only thing is that, well, this is a calculation for the moment in symmetric and neutron matter, and well, one have to impose in principle the stability conditions to see how this really go in a more realistic scenario. Now we go to the 3 body forces. So again, this is a natural solution that comes from the fact that, well, you know that 3 body nucleonic forces are important in ordinary nuclear physics to reproduce the properties of light nuclei. And if you want to reproduce properly the saturation properties of infinite nuclear matter using a non-relativistic many-body approach, you need them. Otherwise, it's not possible. But the important thing is that in the NM sector, you have repulsion at high density. So the question is that maybe for the hyperon path, something similar happens. So maybe if you add some 3 body forces in the high density region, this can introduce a repulsion. I have to mention something here, because most of the time when people mention 3 body forces, they only mention the lambda and n. But in a real scenario, on a neutron star, this is just one of the possible forces, because if you have the complete octet of baryons, then you have lambda, lambda n, lambda. You have basically 2 nucleons, 1 hyperon, 2 hyperons, 1 nucleon, or 3 hyperons, 1. And then you can imagine this is quite complicated because there are so many 3 nucleon forces that it's going to be complicated to get 5 minutes, but okay. So let me do a bit of historical overview of the idea. So the idea, in fact, was introduced 20 years ago, just much before the observation of 2 solar masses by Takatsuka and collaborators, and in a couple of papers, the first one in 2002, and then there was a second one in 2008. And the motivation was that already at that time, microscopic calculation with realistic hyperonuclear interactions were not able to even to reach the canonical value of a Hulse-Taylor pulsar, the 1.44. So they already proposed that maybe 3 body forces can, okay, at that time nobody was speaking about hyperon puzzle, but there was already a puzzle mostly for the microscopic models. So they proposed in this paper a kind of 2 pion delta excitation type mechanism, and in fact they get an increase of the mass, and the masses they reach were compatible for below 2 solar masses, but at that time that was not a problem because nobody have observed in 2002 and 2008 these 2 solar masses, but they were happy because they were larger than the canonical one. Then after 2010, so when these 2 solar masses were already observed, many more people were started to be interested, and there was a first paper that was done during my Portuguese period of life, where basically we make an estimation of the effect of these 3 body forces. So this is a mixture of a microscopic Bruckner-Hartree type calculation for the 2 body sector plus a very simple contact density dependent curve type forces that account for the effect of 3 body forces. And in this case, we were taking into account n hyperon and n hyperon. And basically, that was phenomenological with some 3 parameters that, and in particular, what we were interested in is, well, we were changing the strength of this force from the limit where there were not 2 body forces, 3 bodies at all, up to the limit in which we use a kind of universal 3 body force for the hyperons and nucleons. And when you did that, in the end of the day, the mass that was obtained was larger, but still below these 2 solar masses. So it was 1.6, unfortunately. Then there was a paper by Yamamoto and collaborators when they introduced the idea of this multi-Pomeron potential as a model of a kind of universal 3-body, multi-body repulsion. And they did this in the context of J-matrix calculation using these extended soft-core 9-Wegen potentials, and they were able to reach 2 solar masses, including hyperons, and at the same time, they also were able to reproduce more or less properly the properties of hypernuclei with a relatively moderate repulsion. They don't really need too much repulsion. And I want to stress that because then came a very famous paper that has been quoted many, many times by many, many people that is, in my opinion, and I'm very sorry to say that, not completely realistic. This is the following. This is this famous paper by the Monte Carlo people. So in this paper, essentially, what they did is, first, they describe neutron star matter simply as a mixture of neutrons and lambdas. There are no protons, there are no leptons, so only neutrons and lambdas. And they use a very simple, and this is the trick, the point, very simple interaction models already for the nucleon-nucleon and nucleon-nucleon-nucleon pair, or neutron, because they only, which is this very simple version of the argon potential, the AB prime, with a Urbana-9 force, together with a very simple two-body lambda nuclear interaction, which is Bodmer-Guzmani, supplemented with a lambda NN force, which was basically a two-pion exchange for a phenomenological force. And then they consider two models for distributive force with some parameters which they adjusted in order to reproduce the binding energies of hypernuclei. They found that of the two possible parameterizations they considered, there was only one that was compatible with the two solar mass, but the solution, in fact, was that when you look into the composition, there was no lambdas at all in matter. So there was just pure neutron matter. But be careful. The point is that they have a very extremely large repulsion. And this is as a consequence that the two-body part that they use was predicting an extremely attraction for the lambda in symmetric matter at saturation. It's about minus 100 MeVs. So that is why I mentioned, be careful, because the conclusion they extracted is that three-body forces are fundamental. Okay, it's true, they're important. But we'll have to be careful with the number they get it. And then they came again with us, now in my Catania period already, where we did something similar but a bit more realistic. So we consider neutron matter, in this case, really beta-stable matter, so made of neutron, protons, electrons, and muons and lambdas. We consider, and that was the weak point of our calculation, chiral effective field theory to describe the nucleonic pair and the lambda NN interaction. Unfortunately, not the, oh, sorry, I am just finishing. Not just the two-body part, but we simply didn't have it. And with that, we were able to obtain two solar masses, still with a finite concentration of lambdas in the system. So it's possible to obtain a neutron star with two solar masses and still have lambdas in there. And we also, for free, without doing anything, we compute the properties of medium and heavy hypernuclei, and we improve the description. And again, we didn't need too much repulsion, just about 10 MeVs at saturation, which is in agreement with what Yamamoto found, and it's in agreement with what I will found later, that Bram will mention later. So, okay, now one of the last works is the work made by Wolfram that I think you will mention, you will talk about that tomorrow, where they did a Brunner-Hatteford calculation using completely, in this case, forces derived from chiral effective field theory. The calculations are in symmetric and neutron matter, and again, they also obtain a relatively moderate repulsion for the lambda NN, which is not so much. And the results are also promising because, well, in this case, they indicate that the presence of lambdas is, well, probably unfavorable. Okay, that is the solution. And last but not least, there is a very recent paper by Abraham and Nelly, where they try to extract constraints on the lambda NN force from the, and probably the complete solution is a combination of the effect of three-body forces with other things, in particular the two-body sector that people from Bonn, Jülich, and they show that it's also repulsive. Okay, I have, well, okay, that is the solution, but let me move to the end. So let me thank you again for the attention, the organizers, and again, the Horizon 2020 program for the support.
Thank you very much. We have time for 2 short questions. Who will be the first? Please.
Thank you, Isaac, for this nice talk. If the three-body force, you cannot really know yet how is the amount of three-body force by looking at the properties of neutron stars. Are there other, like the mass, are there other properties of neutron stars like cooling and so on that could tell you the amount of hyperons that they are present there?
The amount?
The amount, yeah, whether... I mean, whether there are hyperons or not.
hyperinfraction.
Whether there are
Yeah, yeah.
hyperons or not. This is the
Well,
question.
but for that, I mean, the fraction is obtained when you impose beta stability conditions. Then, of course, then you can solve, it's complicated because if you want to do cooling, there are a lot of ingredients that are not completely well, also not under control. In particular, the pairing gaps. So if you have hyperons, of course, they will have additional cooling processes that, in fact, they lead to fast cooling mechanisms, and sometimes too fast. So you have in some way to this you have to take into account also hyperon gaps because with the specific heats and the neutrino emissivities are going to be reduced. And this is also again, this depends again on the composition. So if you want to, you can also get, not direct information, but with your model you will do a calculation, you will predict some cooling properties, and then you compare.
Yeah, okay, so...
But
so the point
I
is
mean,
that
everything depends on the composition, of course. Now, the way you can extract the composition by looking, for instance, to the cooling curve, I don't know.
No, more
don't
than
think
extracting
so.
the composition, getting to know finally whether hyperons are present in neutron stars,
Well,
I guess
for
that
sure,
you need
well-
a combination of observables to...
Well, for sure. For instance, the other, I didn't have time to mention, but most of the people have been always just interested on the question of state. But for instance, if you look into transport coefficients, and these are very important for cooling or for other things, for instance, this is just thermal conductivity and shear viscosities. And as soon as you have new species, of course, your thermal conductivities and other transport coefficients depends on the composition. And then, of course, if you can measure, in this case, for instance, thermal conductivity, you will be using from cooling calculation, the shear viscosity you maybe can use if you want to study the oscillation modes of, and this can also be obtained. So oscillation mode with, in particular, this rotational R mode, so you have a star that is basically, you cannot rotate at an arbitrary high frequency because there are some unstable modes that can be created, and then they lead to the emission of gravitational wave, with much less intensity. And of course, everything depends on the ingredients you put inside. So
Shall we perhaps discuss this?
Yeah, but there was
a little
another
bit?
question, I think.
Yes, there was another question.
Don't give the answer so far, so long. I mean, you mentioned that one possibility was, to correct, the hyperon-hyperon interaction by introducing vector exchange.
Yeah.
But it is curious, because, at least I don't follow that closely, but in the nuclear-nuclear interaction, from the times of, Mach-Light, they already included the rho and omega exchange. So...
Yeah. But this is, this has been mainly done in these relativistic mean field models, and the meson exchange they include also the omega, is the phi meson, that they couple only to the hyperon. So this is an additional repulsion coming from this additional meson, in some sense.
Okay. I saw the last question, but really, really short.
Question will be short. I hope the answer also. Isaac, everybody is concentrating on the hyperons, but there are other excited
Exactly. Yeah. You can
states,
have delta isobars. So
yes,
sure.
including our own work. So, but one forgets simply about deltas and other and star.
In fact, this is something a bit historical. If you go to some papers from the 20, 30 years ago, there were people put in deltas. Then at some point, nobody else cared about the deltas, and now they come back again in time. But it's true that, let's put it this way. Everything that is not forbidden to be present in the star, a priori should be taken into account.
And that has a similar effect in the hyperons, actually.
Sorry?
The presence of these excited nucleons, they have a similar effect on the hyperons.
Exactly,
Yeah,
exactly. In fact, there are some papers that they analyze this possibility of delta, of having deltas, and they have exactly the same problem. So they, let's say, shift the onset of hyperons, but the introduction of the delta makes the question of state soft. So you have a delta puzzle in that case, something like that.
So,
Okay, shall we carry on the discussion at coffee? I would like to let us thank Isaac again. Or the next talk will be by Laura Tolos, and we are looking to hear about strange mesons in nuclei and nuclear stars.
Okay, I can take it out. So, hello everybody. How does this work?
It will come in a minute.
I will come. Okay. Okay, great. So yes, so thank you very much. I mean, I'm very happy to be here, and actually now I'm going to move, okay, from baryons to mesons, and I would like to, make I'll give you a brief idea of things that have been done in the field, and in particular, I would like to concentrate on matter, okay? So basically what happens with mesons in matter, and also just to move, to experiments and observations and what has been done in that direction, in particular for heavy ion collisions and neutron stars. So, but first of all, of course, I have to introduce a bit on the anti-kaon nucleon interaction. And also I will briefly mention the anti-kaon nucleon bound state. Actually, all this anti-kaon nucleon interaction we have already, this is also an old version, but okay, whatever. We have heard yesterday morning by the talk of Angels, and also in the session in the afternoon, so this was corrected in the latest version. And anyway, we just heard about anti-kaon nuclear interaction and the lambda 1405 and the fact that governs the isospin 0 channel. And of course, as also we heard, it's an idea, I think by Eulogio, it's an idea already in the 50s by Dalitz and Tuan. And of course, since the 90s, this has been extensively studied, okay, using unitarized theories. In chiral Lagrangian, so here it is a list, not complete, of people working on that over the years, and also on meson exchange models, okay? We always forget that also in meson exchange models, we're giving you information on the anti-kaon nucleon interaction. And in particular, if we reduce, to talk about the chiral Lagrangian, so we have, improvement, of course, since the early works at the end of last century. So having more channels next to leading order corrections, as we also heard from Albert yesterday. And then also Born terms going beyond the Weinberg-Tomozawa, which including better fits, also higher partial waves. So this has been, being still developed. And as I said, there was an extensive talk yesterday afternoon, and I think on Friday morning as well. Now, one of the things that also was discussed yesterday is about the lambda 1405 and the double structure. And here, just to show you, some results that actually are in the PDG about this tupole. Also from Eulogio, we have a more updated graph yesterday on the different solutions of the different groups. And just to show you that I think, as Eulogio mentioned, there is really this, it's within the community is understood that there is these two poles, okay, one coupling mostly, to the pion sigma, while the other one to the anti-kaon nucleon. And here just an example of this spectra, okay, of the different reactions, K minus proton going to pion, pion sigma 0, and pi minus proton going to K0, pi sigma, and to see, that these two reactions are more sensitive. The first one, the K minus proton, the kaon induced to the first, to the higher energy peak, while the second one, the pion induced, is more to the second one, okay? Now, this was just very briefly, but as I said, yesterday we have an extensive session, and I think on Friday morning as well. And now I just wanted to move also to the anti-kaon nucleon, and the fact that if we have, this lambda 1405, so we have an attraction here in this channel, so it's in principle possible, to have bound states of anti-kaons with more nucleons, like in the anti-kaon nucleon case, or also, as I heard yesterday by Nina, by also maybe the 2,4-body anti-kaon with 3 nucleons, okay? So in the case of the anti-kaon nucleon, just a brief summary, has been thoroughly addressed theoretically with chiral models, with phenomenological models, with Faddeev or variational models. So at least from the theory point of view, has been really extensively studied. And of course, this also triggered, the interest, of course, from the experimental side, having initial claims by Finuda, Diston, Novelix, which could find some conventional explanations, while others, were not reproduced. And then moving to more recent experiments from Spring, from Lebs, from Amadeus, from J. Park, A15, A17, and like being some of them, confirmed by others, while others may have another interpretation. And just to point out, and I think there will be, and here there was an indication of a next talk, I think on Thursday by Yamaga, and also, Yamaga on this antichaon nucleon-bound state by the J-Park A15, okay, and the latest results actually. Here actually I had a line saying that these results we'll discuss by Yamaga later. Now, this is a compilation of results from the theoretical groups that we had in our review up to 2020. And just that you see that we have binding energy, very broad range of binding energies, ranging from ranging from 9 to 95 MeV, with width decays going to 16 to 110 MeVs. So basically, you see a disparity of values here. Why is the reason? Well, the variety of results have different sources. On the one hand is the interaction of antichaon-nucleon subthreshold. So we have the chiral models which give you lower binding energies because it is less attractive, okay, below threshold, while phenomenological ones are more attractive. Then also the different way of calculating this antichaon, in this case antichaon proton-proton. So we have the use of variational or Fadayev calculations. So all of them, both of them have some, good things and bad things. So for example, the variational, one of the things is they cannot really fully account for the three-body interactions. Well, Fadayev can, but on the other hand, Fadayev calculations use separable potentials. So, there is some issues that introduce, these approximations that also make differences in the results. And there is also more, let's say, newer. This is this coupled channel complex scaling method that combines the merits of these Fadayev and variational calculations, but also it's at, it has a really high computational cost. Now, I'm moving, and this is what maybe I'm more interested in for this talk, is antichaons in matter. And this is also a long story in the sense that since, this antichaon-nucleon interaction and this lambda 1405, we have this attraction. So what happens when you put a many-body system? And we have early works and also more modern ones, but I'm just showing you here a plot of the one paper in the 1997. So on the relativistic mean field models, also on quark meson coupling models. So you see here the kaons and the antichaons, okay? You see here, like, as you move into the density, the larger, this is the optical potential as a function of the density. Well, this is the mass, how it is modified. And you can see that it's strongly modified in the case of the antichaons. Then we also have, another set of models, the phenomenological ones, that are density-dependent potentials that are fitted to kaonic atoms. You can see, this is the potential as you go towards the center of the nuclei, but the values that we are talking about around saturation, are of the order of -100 to -100. Also interesting, more recently, there has been analysis of the antichaon-nucleon scattering using the chiral effective model supplementing with phenomenological antichaon multi-nucleon interactions. And basically, the conclusion was that kaonic atoms test densities not so deep into the nucleus. So then we have to also be careful, okay, with what we take at saturation density within these models. And just to show you, of course, something that is closer to my heart, let's say, interest, which are these unitarized theories, which is basically the idea of solving, doing a self-consistent coupled channel analysis. So basically, it's like solving a similar equation as you have, in free space, the scattering matrix, but in the medium. And basically, the idea here is that you have this effective interaction where the intermediate propagator has information on the medium. Okay, so it has. We have two-body particles propagating here, and then you have to take into account that if you have baryons, you have to have Pauli blocking, and also mesons and baryons have to dress accordingly to the medium. This effective interaction, as you can see, depends on this meson dressing, and of course you have to solve the equations for this dressing. In particular, if you're looking at antichaons, you have to solve this type of Dyson's finger equation, okay, where you enter the effective interaction, and therefore you have to do this in a self-consistent way because the effective interaction depends on the medium propagator, and then the medium propagator is the effective interaction. So this is the self-consistent part, okay, as you probably all of you know. And also the idea of the coupled channel is you have states that have the same quantum numbers, and if you have an antichaon nucleon, you can have pion lambdas or pion sigmas, okay? Just a brief introduction for those who doesn't know anything about that, which probably are few. But okay, the idea is that with that, you can extract the information on the antichaon in the medium. You can extract information on the spectral function. Somehow this is kind of a probability of finding the antichaon in the medium. So basically, you know that the antichaon, okay, it has a fixed mass, okay? In free space, it has a mass of around 500 MeV. Now, if you put this antichaon in a medium, it develops, you know, a width. It develops, you know, a structure here. I mean, this is what it develops. This is as a function of the temperature. And this upper plot and lower plot, the difference is the the different density, okay? The interesting thing here, for example, if we are looking at this plot here down, you see you have the quasi-particle peak, which is actually this maximum, okay, where the maximum probability of finding the antichaon in the medium, which is shifted. So this is giving us this modification in mass. Whether how wide this function is, it gives me the width. Okay, but also it's interesting that you see it's not completely right-Wigner because you have some excitations, particle Hall excitations. This is the effect of the lambda 1405 on the right-hand side, and also some other excitations, in this case, of baryons with holes, okay? Why I'm showing you that? Because just to show you that this is not only a mass shift, it's also a change in the width. And this also can be extracted within these unitarized theories. And as some points that are interesting to be done is that the S-wave antichaon nuclear interaction, as I said at the beginning, and we know is governed by this lambda 1405. But it's also important that if we go to higher partial waves, we also heard that yesterday, but in particular, it's important also in medium because heavy ions, you know, matter for larger momenta. And then it's also important to have a control on higher partial waves, okay, on the interaction. So now I'm going to the experiments, and I'm just going to point out, as I said, heavy ion collisions and talk about a bit of stars. Nothing said about conic atoms. There's going, I think, to be also talks on Thursday, I think, on conic atoms. So here I just wanted a brief slide of what people have been, you know, doing heavy ion collisions. Of course, it's not all the literature, just to show you a few examples. So the idea is that they have also been worrying about strangeness production in matter. So going, you know, heavy ion experiments from lower energies, from SIS, GSI, to larger, you know, LHC or RIG. And of course, the future, FAIR, NICA, BESS, JPARC, and so on, okay? So the idea is, of course, you can have low energy heavy ion collisions in the sense that the beam energies are, you know, lower, and then you have here these collaborations, CHAOS, FOPIS, ARES, analyzing all these and more particles with strangeness, or heavy ion, STAR, ALICE, and RIG, and others, you know. And of course, the future, the future and also already going on, of experiments that also will address the strangeness. So, what were the conclusions, let's say up to now, but this is being changed already these days, in the sense related to strangeness. So we have antichaons and chaons. So there were some conclusions from analyzing different transport models, which is the theory part, just to compare with the experiment, of course, and some conclusions regarding the mesons, the chaons and antichaons. So on one hand, we have that the K plus seems to be a good proof for the equation of state and giving us kind of a soft equation of state. Why is that? Because chaons are produced at the initial, at the beginning, and then they don't interact so much with nucleons, and therefore leave where they were created without so much rescattering, and therefore they have information on this high dense part and high temperature part when they were created, okay? Therefore they can prove, you know, the equation of state of matter at this moment. Antichaons is another story because they interact strongly, And then we have also some information about when they were produced. So here, the K+, it seems to be in these initial nucleon-nucleon collisions, and then you have K+ hyperons and nucleons. Whether the K- were produced in more secondary reactions, K- nucleon going to pion hyperons. Of course, because of the interaction, okay, with the medium, they exhibit different freeze-out conditions. And also, interestingly, of course, this is what maybe I'm more interested is, the repulsion felt by K+ as compared to the attraction felt by K-. But there was more recently, the fact that what is the role of the phi mode going to K+ and K-, because in particular, there has been analyzed by the FARES and FOPI collaborations. So even with this channel, it seems still we have, this medium potential of the K+ that is still, they found this repulsion. But on the other hand, about the K-, the fact, how the phi decay is actually affecting, the information we can extract out of the antichaons interacting with the medium, because it has actually a strong effect. And maybe some of these informations that we had, or we believe we had on antichaon-nucleon, are being reanalyzed. And actually, what it was needed and was this conclusion in 2017, and as far as I know, I heard some talk like 2 weeks ago, they are getting results from the ADES collaboration on how, this K- is how the channel affects the K- production and what can we say about the antichaon-nucleon interaction. Okay, here I'm just showing now one recent result on production of kaons and antichaons in heavy ion collisions within a transport model, this PHSD model, and comparing with data that we had up to now from these different collaborations. And just that you have an idea of some of the conclusions, that of course, if you have larger nuclei, so they were for different collisions, okay? From different nuclei, and basically the nuclear effects are larger and more prominent if you have larger nuclei. Then also the kaon or antichaon production depends on this on the interaction. So basically, the antichaon is enhanced the production because of the broadening of the spectral function. So basically, this model implementing the spectral function, okay, of the antichaon in matter, where the kaons the production was suppressed in medium because of the repulsive character, okay, of the kaon-nuclear interaction. Also kind of expected somehow, right? But then you have some other analysis of observables like kaon spectrum and antichaon spectrum, or direct and elliptic flow. And then, of course, this also was varying depending on if you look at kaons and antichaons because of the different interaction with the medium, okay? And again, as I said at the beginning, if kaons can prove the equation of state, so here it seems that it was giving a compressibility model of around 300 MeV that was compatible with the data. Now, going to talk about very briefly, about kaon condensation, just to show you what people have been also doing, in neutron stars. We had this nice talk by Isaac on neutron stars. So I'm just going to give you the brief idea what this kaon condensation is. So basically, the idea is that if antichaons feel an attraction in the medium, can condensation happen in neutron star? What's the idea behind? If you think about neutrons and protons, you have this beta equilibrium. So neutrons, proton going to electrons and antineutrino, and this is understood in terms of the chemical potentials of the neutron going to, equal to the proton and electron, and this is how you get your composition in the star. But now, if you think instead of having electrons of having K-, you can have these kind of reactions, which means also, kind of a relation between the chemical potentials. The idea, of course, is whether this reaction is favored or more favored energetically than this one. And this only can happen if the chemical potential of the kaon is smaller than the chemical potential of the electron. So if you think of the chemical potential of the kaon as the mass, this means lowering the mass drastically, okay? And of course, the idea is if this happens at certain density in the star, then we will have kaons or antichaons, and then we will have a condensate, okay? So this actually, it's an old idea, and at the beginning, because of this really large, drastic change in the mass, this was considered not irrelevant, okay? So we're talking about, this early paper of Glendenning. And now, Kaplan and Nelson came, and this also pushed, the field on the anti-kaon-nucleon interaction, on the fact that it could be strongly attraction. And then lots of papers start appearing, end of the last century, on this renewed interest on the anti-kaon-nucleon interaction and the fact that whether we could have kaon condensation, okay? And then you see here some examples, the fact that having kaons softens the equation of state. So these are for different values of the optical potential of the kaons on the equation of state. Also, this led, of course, to the lowering of the maximum mass if you have a softening of the equation of state. But this was not, of course, the whole story, because you might have hyperons, as we heard. And then if you have hyperons, the idea is that kaon condensation is more difficult, okay? Because you don't need so much electrons in the system. So basically, your electron fraction is decreased. If you have another particle that's negative, then it's going to have the role of the electron. And therefore, it led to the fact that this relation, between chemical potentials of electron and kaons was not so favored, and it was pushing the appearance of kaons, okay, to larger densities, the fact of having hyperons. But in any case, now, over the last years, people have improved, especially in the relativistic mean field models, trying to see whether we will still have two solar mass observations and have, also study proto-neutron stars called collapsed supernova neutron star mergers. And just examples, here you have some relativistic mean field models by the group, here of Banik and Bandyopanday on this possibility of having kaon condensation with nucleons. So you have here, these two solar masses, and we're still having kaon condensates. Of course, the anti-kaon potential is of the order at saturation density of minus 120 MeV. Here you have another group which has a slightly different model, not density-dependent couplings, but higher-order couplings with nucleons. Also kaon condensates, but not hyperons. And when you put hyperons, if you look at this one, you get a softening, but still, you have to look the opposite of the other, okay? This is the mass and this is the radius. But okay, you have, again, anti-kaon optical potentials of around minus 140. I'm over it already. So, and then you have more recent ones also, again, having these two solar mass observations, but still potentials very, very strong. And this is one of the last ones, including deltas. We were discussing about deltas. And trying to see how the observations go, gravitational wave, also millisecond pulsars. These plots here, these boxes here are from NICER. So it's still, the possibility of having all these species, nucleons, hyperons, deltas, condensates. But again, if you look at the anti-kaon potentials that are using as around 100 MeV at saturation. So from the point of view of unitarized theories, going back, this means lowering a lot the mass. And as we have seen within chiral models, this is actually very unlikely within these microscopic unitarized theories. So, okay, this is probably my personal point of view. Well, within the unitarized theories, kaon condensation seems very unlikely, and from my personal point of view as well. But anyway, I wanted just to point out the possibilities that people are dealing with. And I'm done. So basically, I just try to show you, a bit to understand, that is important, this anti-kaon-nucleon interaction, the presence of the lambda 1405, the fact that people have invested a lot, and we are still investing a lot in understanding this lambda 1405 and bound states of anti-kaon with clusters. But again, I think it's an interesting field also to go still to matter, in particular for heavy ion collisions and neutron stars. So thank you for your attention.
Thank you very much. And now questions. Questions?
Thank you, Laura, for this overview. What is your personal opinion on getting information on the kaon optical potentials, K plus and K minus optical potentials from heavy ion collision experiments? How is the situation?
Well, my personal point of view for the K plus, it seems that there's a certain agreement that there is this repulsion, 20, 40 MeV. So because they don't interact so much, I think the reactions are more clear. This is what I see from abroad, okay? Now, anti-kaon-nucleon is still a mess, I think. There are some observables that look okay if you put attraction in the anti-kaons, other not. And now it comes, as I said, this phi decay into kaon and K minuses that it seems is also messing up the whole thing a bit with the antikaons.
So the transport models are now being further developed and so
Yeah,
on?
so they are basically, well, this was one of the first ones. I mean, they put this full spectral function, and yeah, they are trying not only to put mass shifts, but also widths. And, but still, I think it's complicated to extract something about the antikaons. But okay, maybe I should ask a heavy ion guy. So.
Okay, next question.
So about the antikaons in nuclear matter, actually there are also measurements for antikaon absorption of nuclei with pion beams,
Yes.
right? Where people have measured differential production of antikaons, phi, and kaons in the same experiment. And now I'm actually very surprised because there are the data are there already since I think 3 years. But there is no calculation, including the medium spectral function that you and collaborators already calculated many years ago, right?
Yes.
For antikaons, for a simple, let's say, system as pion nucleus, right? And I wanted to ask you, what is, let's say, the complicated aspect of this calculation? So why? Because I know there are some groups in Frankfurt, I think, that could do this.
I know.
But it's not done. And I am curious to understand what is now, let's say, what is preventing the calculation? What are, let's say, the technical aspects?
I don't know if it's manpower or changing the evolution codes in order to put all this more, fancy, if you want, not more complicated, but,
more complete spectral
more complete
function.
or more, a spectral function you need. How it, of course, evolves with time, so more densities, more, the width is not only the width, it's not a parameter, so you have some density dependence, some temperature dependence.
So finally, this is not done yet, finally. So these spectral functions, they are not really implemented full-fledged in this transport code.
In the PhD, yes. I mean, Elena has been trying to do that. There's some issues there. I know the URQMD, I don't think they have done it yet. And in SMASH, I don't know if really they
don't
can,
think they have
do
nothing
that.
like that.
So
Okay.
I think it's a technical issue more than anything.
Hopefully at some point it will be overcome.
Yes.
Okay, I think we will have to move on. Let us thank the speaker again. And we are coming to the last talk by Onishi-san, and he will talk basically about the Hyperon puzzle and his view of it. So, thank you. You can start.
Okay, thank you very much. First of all, I'd like to thank the organizers for giving me an opportunity to present our work in progress. And this work is based on a collaboration work with Jinno, my student, and Murase and Nara are heavier specialists. And I'd like to talk about the lambda flow from heavier collisions and the Hyperon puzzle in neutron stars. Okay, I first introduced what is the Hyperon puzzle, but this part I hope I can skip. And the lambda potential from chiral EFT, and the result of the directed flow of lambda particles is shown. And summarize my talk in the final slide. Okay, Hyperon puzzle is already reviewed by Isaac Bidania, and attractive lambda potential and the nuclear matter causes hyperonic matter equation stay softer, and we cannot support two solar mass neutron stars. That is the Hyperon puzzle. And there are three solutions of three solutions. The first one is the three-body lambda repulsion, which is repulsive, and lambda potential at high density becomes stiff, and we can support the two lambda does not appear, and we can support two-star mass neutron star. That's the first possibility. And the second one is the transition to quark matter before hyperon appears. That is the second possibility. And the third possibility was not mentioned by Isaac. There is a possibility, if we cannot, two possibilities are denied, then we may have a conclusion that we have to modify the general relativity. But as a nuclear physicist or a hadron physicist, we want to pursue the possibility of the upper two, and I concentrate on the first possibility in this talk: three-body lambda-lambda repulsion, or the lambda potential at high density to solve the hyperon puzzle. Okay, the repulsive hyperon potential at high density was derived in chiral UFT by these people, Gustanger, Kaiser, and Weise in 2020. And also the Michio Kono gave some estimate of the lambda potential at high density in using chiral UFT. And chiral UFT is a first principle theory, but not ab initio. I mean that we have to choose the parameters to explain the data. And also in these calculations, they have one, in the case of Gustang, Kaiser, Weise, they have one parameter to choose the stiffness of the lambda potential at high density to support or to avoid the hyperon puzzle. And also in the case of the Kono, they have, he has parameters, okay? And therefore, they are not, in a sense, ab initio, and they need to be verified at high density, for example, by using Hebbian collisions. And in order to probe the high density equation of state, people usually use the collective flow. In old days, in 80s or 90s, people started to use the side flow px average to evaluate the stiffness of the equation of state. And recently, people use more about the so-called directed flow, which is cosine theta, theta Archimedes angle average. And when two nuclei collide with each other, and there is a dense region, then the nucleons tend to avoid this dense region because of the high pressure, and the forward-moving particle will have a positive px or positive v1. That is the directed flow. But in 2014, there has been a puzzle raised by the STAR collaboration, which says that the proton-directed flow shows a non-monotonic behavior as a function of the colliding energy. And that non-monotonicity cannot be described by any of the transport model calculations at that time. Therefore, there was a doubt that we cannot discuss the equation of state from the directed flow. But last year, we have found an explanation. And which says that this directed flow is composed of two components. First one is the compression stage, where the positive slope of the directed flow is caused. But when tilted matter is formed in the expansion stage of the collision, then this emission in the higher pressure gradient direction causes negative slope in the directed flow. And the combination of these two contributions gives rise to this non-monotonic behavior. And therefore, the proton v1 slope puzzle is solved. Now, let me access to the equation of state, or the lambda potential at high density. Okay, and in words, since the directed flow of protons can be described by a single equation of state now, and therefore lambda potential at high densities may be constrained by using the lambda flow. That's the idea. And we study, therefore, the lambda flow using the lambda potential from chiral UFT. I think at least this is complementary to the high precision hypernuclear spectroscopy. Okay, lambda potential from chiral EFT. Let me discuss a little. And Pet shower, Heidenbauer, and Kaiser, Meister, Weise. And later on, Gustang, Kaiser, and Weise developed the so-called decoupled saturation model of the chiral EFT. In the chiral EFT, from the next to leading order terms, then we have the 3 baryon repulsive, or not necessarily repulsive, 3 baryon interactions. But when we assume that these diagrams are saturated by the decoupled propagation, then we can introduce the several parameters fixed. For example, the delta decay into pion and nucleon, or the sigma star decays into pion and lambda, or something like that. Then we can fix one parameter. And they also use the lambda potential at normal density to be minus 30 MeV. And then we have 3 low energy constants, but only 1 remains. And they tune that remaining parameter to avoid the hyperion puzzle and construct the potential at high density, like this. The lambda single particle energy does not touch the neutron chemical potential, and hyperion does not appear in neutron stars. That is the idea. In addition to the density dependence, we also have to take care about the momentum dependence of the lambda, because in chiral EFT, then for the many body force comes from the higher order diagrams, which contains a lot of propagators and low energy constants or derivative. Therefore, the interaction becomes necessarily non-local, which appears as the density momentum dependence of the potential. Okay, the density momentum dependence was shown by Kono in this paper. And in the case of Gerson, then the TUM thesis is found from in the INSPIRE, but not shown in the paper. And the momentum dependence from chiral EFT seems to be stronger than the momentum dependence from the usual lambda n interaction, for example, from the core cluster model calculation. Okay, and we have fitted these momentum dependence by some use of this Lorentzian type kernel, like this. But the cutoff of this theory is 500 MeV or something like that. Therefore, it's not safe to fit the data up to 500 MeV. Therefore, we also prepare only the low momentum part of the chiral EFT momentum dependence. And the density dependence is fitted by using the so-called Fermi momentum expansion developed by the Tuse, Latimer, Onishi, and Kolometsev in the 16 and 17. Okay, therefore, we use these potentials in the Hebbian collision calculation. Okay, let me show the calculated results. Before that, lambda flow slope is measured by the star collaboration between the 3JeV to 3JeV root S to 200 JeV root S. Okay, this is the top energy. And the lambda flow slope seems to be very close to the proton flow, but which is somewhat strange, because in the compression expansion explanation by Nara and Onishi, then we have found that the two contributions are important, but we do not have lambda in the initial stage. Therefore, the compression stage effect should be small. Therefore, I expect that the lambda directed flow is smaller than protons, but it is very similar. Then one of the explanations is that the lambda potential at high density is stiffer than protons. That is one of the possibilities, okay? Therefore, it may be possible. And transport model calculation. using an updated event generator JAM 2.1 is utilized for this calculation. And there are several updates, which is very, how to say, technical and detail. I don't want to explain the detail, but for example, the collision time scheme is updated according to the Zhao et al. 2020, who are the developer of the ZPC cascade code. And this time we also include the quark potential of leading hadron during the formation time. Up to the formation time, I mean the string breaking, then people usually do not include the mean field or collision term during the formation time, but we found that it's better to include the quark potential during the formation time in the lambda calculation. Okay, let me show the result. This is a result at the colliding energy of 4.5 JeV. And the black point shows the result of the star collaboration. And the black line is the result of the cascade calculation without potential effect, mean field effects. And the standard potential for lambda may be the nucleon potential times 2/3. That roughly explains the data, but at forward angles and backward rapidities, then they underestimate the data. Okay? And with the chiral EFT 2 and 3 body force lambda potential, then this red line well explains the data from backward rapidity to forward rapidities, which also applies to the heavy ion collisions from 3 JeV to 27 JeV. Okay, it's very good. But in the case of when we include the momentum dependence, then we underestimate the data to some extent. That is the problem. And finally, let me show the colliding energy dependence of the directed flow. And the black point shows data. For protons, we can well reproduce this slope, energy dependence of the slope. For lambda, this one, and the result with the chiral EFT lambda potential fit best the experimental data very well. But when we include the momentum dependence, then we underestimate the data. I don't know why, but anyway, also in the case of the proton, then we slightly underestimate the slope at 3 JeV, and when we increase the when we use the stiff equation set, for example, for nucleon potential, then it may be closer to the data, I hope. Okay, this is the situation. Okay, let me summarize this talk. The directed flow of lambda from heavy collisions is studied by using the lambda potential from chiral EFT with 2 and 3 body interactions. And first of all, I'd like to say that the directed flow of lambda is sensitive to the lambda potential at high densities. Okay, and at the lambda potential from chiral EFT, density dependence of the lambda potential from chiral EFT with no or weak momentum dependence is consistent with the directed flow data from heavy ion collisions, which was already discussed by Zhang et al. Only for 3 JeV, but for higher energies, this is the first. And the forward but the later points are minor. But anyway, the momentum dependence of lambda potential needs to be evaluated carefully. And no momentum dependence fits the data very well. Therefore, the M star effective mass of the lambda may not be very small compared with the bare lambda mass. And the forward-backward directed flow values seem to be more sensitive to the lambda potential at high densities. And okay, let me skip this one. Then, in order to pin down the lambda potential at high density and to solve the Hyperon puzzle, we may need more data of directed flow. with wider rapidity coverage, which may need the beam of root S of 3 to 10 or something like that, or 3 to 5, which really corresponds to the FAIR or NICA or JPAC high. And other things may also apply. Okay. Thank you very much for your attention.
Thank you very much for a very interesting talk. We now have plenty of time to discuss. Please.
It's very nice work, Akira. So I was wondering whether maybe the ADES data could be used for this measurement of flow, direct flow of lambda. So maybe, I mean, I don't know if Simon is listening. I mean, you showed yesterday that you have like gold, silver data. Can you measure precisely direct flow, V1 and V2 for lambda with ADES? Is it possible? Because they have plenty of hyperons producing heavy ion collisions at 1.2 AGV, and hence they should, I mean, it's all about probably the resolution of the reaction plane. But in principle, you could already use this data, you know, the measurement of gold, and silver, hyperons production. They even have sigma zeros, actually, to my understanding now. So, well, in PLED. But okay, lambda for sure you have. So now it would be very cool to measure the flow there. And
First of all, for the directed flow, many of the transport models fail to explain the energy dependence of the directed flow. From 7 JeV to 15 JeV or something like that. Therefore, at present, our code is only one code which explains that energy dependence. Okay?
Exactly, and
for other direct particles such as sigma or xi or something like that, then of course we can calculate, and we have that calculated data in the hard disk, but I do not show. And of course, I want to discuss if the other hyperons flow is existing, then I'd like to compare. And what was your real question?
yeah, well, if your code works at 1 GeV, basically. Because the ADES data are at 1.2 GeV, right? So it's a bit, I mean, a bit lower in energy than what you have looked up to now, right? And the question is whether you think this will also work at 1 GeV, because then if it works, you could, you have already this data, because the hyperon identification with ADES is very good. That's what I wanted to ask. So does it work?
I think that it is possible to compare the result of the other existing data. That's right. But many of the data, for example, as you know, it's the particle identified lambda is not easy to handle. Therefore, I think that we show the data of all the directed flow for this energy region by using by the Stark collaboration. But as for the directed flow, I think this is all. And what is necessary is that the directed flow is strong in the colliding energy region of 3 to 10 JeV or something like that. For the ALICE data, then it is far away from here. Therefore, maybe it may be necessary to compare the directed, elliptic flow and the hyperon, calculated one. And with
HADES, you know, the experiment at GSI that we heard yesterday in the second talk of Simon Spies, I think.
Okay,
That's-
for Hades and E8095, then they have the data of PX average, not V1. And I know that, and we can calculate, and we have the calculated data in Hades, but I'm sorry, this is 15 minutes talk, and
Okay.
we cannot show.
Okay, shall I suggest that this discussion may be carried on at coffee? There was another question over there.
So you mentioned that with the inclusion of the three-body force lambda NN could be a solution for the hypergopusor, but from the Cairo EFT, I think that the coupling from lambda NN to sigma NN is so important. So why don't you treat the sigma degree of freedom?
For the sigma potential at high densities, we have used the Corners parameterization of the chiral EFT. That's one thing. And of course, sigma is also important. And to say that, to be honest, this result shows the V1 of lambda and sigma 0. Because sigma 0 decays into gamma and lambda immediately, then we cannot distinguish sigma 0 and lambda. Therefore, this result shows the result of lambda and sigma 0. And the sigma 0 potential is not modified. And that effect is not yet studied. Thank you very much for your question.
More questions? If not, I would like to ask you to thank the speaker again. And this talk finishes this section. So thanks everybody who participated, and let us have a good coffee break. Shall we thank all the speakers again before we adjourn?
the latter half of the morning session. Okay, let's start. So let's start the latter half of the morning session. Let me call the first speaker of this session, Junhui Chen, and he will talk about the recent progress of the global spin alignment, the Phi and the K-star in the heavy ion collisions. And he will give a talk in the Zoom, so please start.
Thank you. Thank you for the chair. And can you hear me?
Yes, yes, we can hear you.
Oh, okay, great, thank you. So first, I would like to thank the organizer to give me this chance. And so as the chair introduced, we will discuss the vector meson global spin alignment in heavy ion collision. And sorry, I can only make it online. So this is the outline. I will start with a brief introduction, then I will focus on the vector meson measurements, and then I will give a summary and outlook. So the global polarization in heavy ion collisions. In non-central heavy ion collisions, large orbital angular momentum is deposited in this reaction zone. The spin orbital currently may yet the global polarization of the quark in these reaction zones. And if this phenomenon, this physics is established, the hyperon or vector meson may present a global polarization. To assess this physics, one can look at the lambda decay, the proton in the decay angle distribution with respect to the orbital angular momentum. And also for the vector meson, for the phi or the k star, you just look at the decay products are also similar to the with respect to the orbital angular momentum in the rest frame. And this dedicated effort has been tried to find this search for this physics. The first measurement was done by Starr in 2007 with for the 200 GeV and the 62 GeV with very large statistical uncertainties. Also at that time, the vector measurement for the phi and the k star was also performed, and both data present large statistical uncertainty, and the claim no signal was found at that time. Continued effort has been done, and there was a very important achievements achieved in 2017 by looking at the beam and its dependence of the lambda polarization from the star correlation, and this is a very beautiful data established the global polarization of global polarization in heavy ion collisions. If you combine the hydrodynamic model calculations, and one can extract the vertical of this fluid, and the value is very high as 10 to 21 per second. So this is a new feature of the quark-gluon plasmas in heavy ion collisions, and this is a cartoon showing the vorticity field in these reactions. There's also new data both from hyperon polarization. This is actually was led by our next speaker, Takafumi, and from Ali's collaboration, and they also measured a vector meson spin alignment. So they present the data in the collision centrality dependence in different PT region. For the low PT, they see signals, and but for the intermediate PT, actually the result are consistent with one third that is no signal within the statistical error bars. And so since the hyperon global polarization already be established, so why we still do the vector measurement? Because there is no local cancellation when integrating over phase space as opposite to the spin 1/2 particles. And second is that we can maybe assess to the spin orbital force. This is termed the spin under the field force and the momentum. So this is also cancelled in the lambda polarization. The third item is that the vector meson, such as the phi meson, are expected to originate from the primordial production. So this can provide a more sensitive to the early dynamics. And this is our result from the beam and scan data at non-central collisions. Showing on the left here are the rho 00 for the phi meson from 11.5 GeV to 200 GeVs as a function of transfer momentum. Showing on the right here are the K star measurement also on the same data sets one can see, once you see that both measurements actually are performed with our the second order event plan with our main detector, the time projection chambers. And if you look at the data, the star here, that we see that the signal for the 5 measurement occur mainly within the 1 to 2.4 GVs. But if you look at the larger PT regions, that actually the result can be regarded as being consistent with 1/3 because there is large uncertainty here. We also perform a cross-check to the 5 measurement global spin alignment with first order event plan, which is done by our detector, GDC or the BBC detectors. And if we want to establish the signal, we actually average over the measuring PTs, and showing here is that result from our data. Then you can see that the 5 measurement actually is significantly about 1/3 for low energy than 62. And but for the K star, actually the result is largely consistent with 1/3. We also can do another average test over this low energy for this 62 GeV. This is the signal we have for our data. So if you look at the 5, actually the signal is very, very, very significant with 8 sigma. But if you look at the K star, it's consistent with non-polarizations. And we also study the fine structure of the centroid dependence. Showing here is that the rho 0 for the 5 measurement as a function of collision centricity. 0 represent the central collisions and 80 represent the peripheral collisions. You can see that the signal are very systematic or larger than 1/3 in this this 27 GeVs. But if you look at the higher energy for this, for example, for the 5, for this high energy is greater than 62 and 200 GeV, or for the K star for greater than 39 GeVs. In central collision, it tends to have the signal less than 1/3. This might be caused by transverse local spin alignment and a contribution from the holistic correlation from theories. And so there is expectation of the rho 0 signal from series, for example, for the quark correlations or the vorticity of magnetic field contributions, the vorticity tensors or the electric field, and all the fragmentation physics or the local spin alignment or the helicities or the turbulent color field. All these expectations give the values less than 1/3 or with a very small value of like as 10 to -4 or 10 to -5. There is a new theory, the so-called vector meson strong force field actually can produce a signal greater than 1/3. I will discuss a little bit more on this theories. And so this is because the polarization in this field is that by this form field is that this is their terms, and so this is the field electric component of this field. This is G component and X component. The coefficients the coefficient in the theory is that they can be fit to the data, and you extract this parameter. This is the fit from our data, and if they also can extract the vector meson field strengths is from our data is that close to 2.5 m pi squared. So the heavy ion collision actually is a very highly volatile environment. So if you look at the nucleus at relative energy and the nucleus at rest, there is a distinctly difference. The bottom cartoons here show the dynamic evolution of a heavy ion collision in the CGC framework. This is the initial of the heavy ion collisions, and this is the formation of the Grun condensate plasma, and this is the hadronization. There is a huge fluctuation of these collisions, so this may lead to the quark and Grun. This fluctuation may lead to the local net quark current. So this is a essential part of the vector meson field. So please allow me to elaborate a little bit. I will not defend model, but I just introduce in something here that like the electric charge in motion can generate an EM field, the SS quarks in motion can generate an effective 5 meson field. And the 5 meson field actually can polarize the strain quark and anti-strain quark with a very large magnitude due to the strong interaction. This is similar to the EM field polarized anti-quarks. So if you write out the formula here, this is the polarization of the strain quarks in terms of the vorticity terms and the EM field turns, and the strong force field turns. A different color represent the magnetic component or the electric component. So we are interested in this turn is that the quark inversions of this strong orbital force, the so-called EM, the vector meson fields. And if you use the model to describe our data, actually this is the first time that strong force field is expanded this spot as a key mechanism that led to the global alignment. The vector meson field is not new yet because it had been used before. For example, if you read the paper by Professor Kapusta's group and the colleagues that actually used the meson field generated by the baryon currents in high energy nuclear collision to explain the difference of anti-lambda and lambda polarization. Those showing on the right are the figures from their papers, and this is their course, their theory. They can describe the data well for the this is for the anti-lambda lambda difference. And please allow me to do in the 200 GeVs. So if you this is the centrality depends on the 200 GeV. This is for a very central collision with distinct deviation from 1/3, actually lower than 1/3. So is that contribution from the local spin alignment dominate in central collision or at very high energies? Although this the vector meson field model can describe, they accommodate a positive deviation in mid-central and peripheral collision. Actually, they also predict a positive signal that not positive. That's greater than 1/3 signal in central collision. Actually, in contradict to the to our data. So it will be interesting to perform the measurement of local spin alignment. So this is come to my summary. STAR has observed a surprising large global spin alignment for the phi measurement. I hope I'm convincing you. But this data cannot be explained by a conventional mechanism. However, this data can be accommodated by a model with strong force fields. Our measurement provides evidence for a quark version of spin orbit force at work. And it provides a potential new avenue for understanding the strong interaction. And there is recently, ALICE posted a new measurement for the JEPSI polarization in lilac collisions. So showing here is that the polarization as a function of the collision centralities, and showing on the right here is the polarization as a function of the transverse momentum. Both data present this very clear signal, although this is actually in a very large repetitive region. So if you put the lambda theta and calculate the rho zero, the magnitude is close to 0.37, it's very large. So the question will be naive to expect how will this look if in the mid repetitive regions. It will be very interesting to see. So this is actually an effort led more than 5 years. So I would like to sincerely thank the STAR collaboration, and special thanks to Declan, Yugang, and Subhash, and Xu, Aihong, and Chen Sheng. So the group make all this happen. Thank you for your attention.
Okay, thank you very much. So we have plenty of time for the discussion. So is there any comment or the question? Yes, please.
Thanks a lot for the nice talk with this overview of these interesting effects. I'm a little bit, I have a curiosity because this comes more from the LHC side than what you showed about the JPSI. Because the fact that is intriguing me is that this effect is actually coming more in the region where we don't expect so much initial state effects. So something like, like initial magnetic or electric fields to matter, but something that comes later because of the charm quark recombination for JPSI. So what kind of effect can lead to this kind of polarization for this low PT JPSI, in your opinion?
Thank you for your question. I have to admit that this is done by Alice, so I didn't involve in these studies. So it's indeed very exciting to look at the data. So for example, as you mentioned, a low PT, but this is also in large rapidity. So yeah, it's not clear to me, although I have read that paper very carefully.
Any other question or comment? Still, we have a few minutes.
Sorry, I make it too fast.
So, okay, may I have a question to you? So you wrote this here, how will be the result at mid-rapidity? So you have some comment about the large rapidity. So what is your guess? So how will it be if you have any some guess or expectation?
From experiment-wise, so it will hard to say that. So the expectation from the so we have to look at the data. But I will expect it will be smaller than the forward rapidity. So if you go to mid rapidity, I will expect it will be smaller than the forward rapidity.
I see.
But I'm not sure. Yeah, frankly speaking, I'm not sure if it go down to 0 or just 1/3 or it will be still about 1/3. This is not clear to me.
Okay, thank you very much. So
Thank you.
Any other question or comment? Okay, if not, let's thank again.
Thank you.
Okay, then let me call the next speaker. Okay, the Takafumi Nida, and he will talk about the global and local polarization of the hyperon in the heavier collisions. Okay, please start.
Right, okay, yes. Hi, everyone. I'd like to thank organizer for this invitation. I'm very happy to be here in this conference and also in this beautiful city. So today I'd like to talk about the polarization measurement in heavy ion collision using the hyperon. So this is also similar to the previous talk. So let me start with a brief introduction. Already Jin-Hui mentioned a little bit, but so here is a cartoon of the heavy ion collision. So you see the two nuclei collide each other. So there are two important features in the initial state, especially for this non-central or non-head-on collision. So first is, of course, the system has a large orbital angular momentum of the order of the 10 to 6 h-bar, which is quite large. And also we have a strong magnetic field because you know that there's a proton inside the nuclei, of course, that carries electric charge and that are moving fast in the beam direction. And actually, the direction of the orbital angular momentum and the magnetic field coincide each other. So which is perpendicular to the reaction plane. So reaction plane is this green mesh. That is defined or made of the beam direction and the impact parameter. That is a vector connecting the center of the two nuclei. So if we have such a large orbital angular momentum, then of course that would be partially transferred to the medium created in the collision. So the system would be rotating or there is a vorticity. So that leads to the polarization, right? So the particle inside the medium would be globally polarized along that direction. I mean the L or the orbital momentum direction. But of course, there might be a contribution from the magnetic field. But in that case, a particle and antiparticle are oppositely aligned because defined sign of the magnetic moment. But for the magnetic moment, the lifetime is actually unknown, but expected to be very short, maybe of the order of 0.5 Fermi. But that also depends on the conductivity of the QGP that is also unknown. So, but yeah, anyway, we can look at the data. So for the polarization measurement, of course, we use a hyperon decay, which is parity violet and weak decay, so that For example, in case of the lambda hyperon, lambda decay into the proton and pi minus, where your daughter particular baryon, in this case proton, is highly correlated with the lambda spin direction. So this is the equation, right? So the daughter baryon distribution in the lambda rest frame. So pH is a polarization, and this alpha is a decay parameter. And yeah, this represents a kind of the sensitivity to the measurement. And in case of lambda, it is around 0.7, but in general, one can use other hyperon. But of course, this decay parameter are different, so the sensitivity also different, but I'll come to that point later. And of course, we want to measure global polarization. So basically, we need to calculate or measure the component along this L direction that again are perpendicular to this impact parameter direction. So the impact parameter direction, or I mean the azimuthal angle of the impact parameter direction is defined as psi1 here. So that can be measured or determined by measuring the spectator fragment. Since we do have the forward detector, so either measuring the spectator neutron or proton, we can determine this angle. So this pH is our definition of the global polarization. So here is a result of the energy dependence of the global polarization for lambda hyperon as a function of the root S. So as you can see, so first this was observed by Stark collaboration in 2017 for collision energy from 7.7 to 39 GeV. And of course, 1 year later, the Stark also revisited the 200 GeV. That was actually done in the 2007, but at the time, the results are consistent with 0. But later, with the high statistics data, we also observed this finite signal. So having this data set, we clearly see the energy dependence. So the polarization become larger towards if you go to the lower collision energy. And also, you see the several line here. So basically, the results are explained very well by a different kind of theoretical model, like a hydro or transport model. So these results indicate the thermal vorticity of the system. So assuming the local thermal equilibrium, so this global polarization can be decomposed into two contributions. So of course, as I mentioned, first is a vorticity term, then this is a contribution from the magnetic field. So you see that this field symbol is for lambda and open is for anti-lambda. So we don't see any significant difference between lambda and anti-lambda, which means that basically this global polarization is dominated by this first term, the vorticity term. And it turns out that, so we can also estimate that vorticity by assuming some temperature, of course, but it turns out that this is the most vertical fluid ever observed. So of the order of the 10 to 21st or 10 to 22nd per second, right? And you may notice that maybe the anti-lambda looks slightly larger than lambda. So there may be a possible contribution from the magnetic field. But for example, previous speaker also mentioned that there are other sources that create the difference. But anyway, we needed to first clarify whether or not there's a difference experimentally. You also may wonder why the energy dependence look like this, because if you go to higher collision energy, you would have a much stronger angular momentum, but that can be explained or understood in the following way. So if you go to higher energy, so the system, basically the two nuclei pass through, and then we can call it the baryon transparency. So basically we have the finite acceptance or detector, and we only measure the mid rapidity region where you see that this flow velocity field is almost symmetric in this impact parameter direction. But if you go to lower collision energy, so our detector starts to capture the whole distribution. And if you go to the larger rapidity region, then you will see this more stronger shear flow structure. Therefore, the polarization goes up. And of course, if you go to higher energy, so the system lifetime becomes longer. So the vorticity of the polarization might be diluted. That also contributes. For example, this model calculation shows such time dependence. And there is also interesting expectation for the lower collision energy. So for example, yeah, starting from this production threshold of the to nucleon, the vorticity start to increase. And as I mentioned, at some point it start to decrease. So there will be some maximum point at certain energy. And that region might be different between lambda and anti-lambda because, of course, at lower energy, the antiparticle is less produced. Or also, yeah, there are other explanations, but yeah. So this is the current result, especially for lower collision energy. Now you see more data around here. So STAR also published the result at 3 GeV, this violet star, and also Hades. I'm showing the preliminary Hades result for 2.4 and 2.55 GeV. So yeah, uncertainty is still large, but it seems that polarization or global polarization still increasing at least down to 3 GeV. And yeah, we know that STAR also took a large data set in the beam energy scan phase 2 program. And for example, this is a list of the collision energy. So we are expecting to have more precise measurement that are fielding around here. And one can also extend the measurement to multi-strangeness particle, like a Cascade and Omega. But of course, challenging here is low production rate, of course, and also the small magnitude of the decay parameter alpha. So here is a table. For Cascade case, the magnitude of this decay parameter is almost half of the lambda. So the sensitivity is much smaller. And for Omega, it's very close to 0. So practically, it's almost impossible to measure directly using this formula. But there's another way. For example, by measuring the polarization of the daughter lambda, one can also know your parent hyperon's polarization. So for example, this is a Lian formula that relates to your cascade polarization to the daughter lambda polarization. And that can be simplified, this equation. So basically, we have this polarization transfer factor C. So in case of this spin 1/2 particle, and for a cascade, it's close to unity. But it depends on the type of the decay. So it could be negative or positive, but in this case, it's almost 1. And for case of Omega, that is a spin 3/2, there's, of course, similar relation here. But the problem here is that this another decay parameter called gamma is not known. So, but alpha is small, and this time reversal parameter beta is also expected to small, and these parameters need to satisfy this relation. Therefore, this gamma should be close to either +1 or -1. So, based on this global polarization picture, this vorticity picture, one could also constrain this uncertainty on this parameter. So this is a current result for Omega and Cascade, only for actually 200 GeV, but this is energy dependence. But so you see still large uncertainty, and but it seems that the hierarchy in this polarization depending on the hyperon. For example, Cascade seems to have almost twice larger than the lambda. And of course, Omega still has a larger uncertainty, so this needed to be improved with future data. But naively, based on the Samar model, we should expect the same polarization for the spin 1/2 particle, so that lambda and Cascade should be same polarization. But for Omega, that should be larger because of different spin. But of course, there are many other complications. For example, different freeze-out time leads to larger or smaller polarization. And we know that the multi-strange particle likely to be emitted at an earlier freeze-out. And also, they have the different contribution from the field down. So all contribute to this result. So the interpretation is still difficult, but interesting is that this transport model captures the trend, basically. And as I mentioned, if we improve, especially this omega global polarization, we could also constrain this sign of the gamma parameter. So let me also mention about the local vorticity or local polarization. So in heavy ion collision, so the situation is very complicated. We do have a lot of things happening, and we do have jet, and of course there's the initial density fluctuation. We have a collective expansion. But for example, if the jet pass through your medium, then along the jet axis, there will be this vortex ring. This is actually a simulation. And for example, we have the initial density fluctuation, and having the larger collective expansion, there may be a more complicated vortex ring or vertical structure like this. But one naive or simple expectation is that flow-driven polarization or flow-driven vorticity, since we know that there is a strong elliptic flow, so that is a stronger expansion into in-plane direction. In-plane means this shorter axis. This is a transverse plane if you look at the collision area. And compared to this long axis to the short axis, we already observed that there's more particle going to this in-plane direction. So naively, one can expect this kind of the vorticity like this blue arrow. So the rotational axis along the beam direction. So this is the polarization along the beam direction. And this polarization, the time the polarization depends on the azimuthal angle. So, and indeed, actually, star collaboration observed such a quadruple pattern or sign pattern of this polarization. This is as a function of the azimuthal angle. And this y-axis is a kind of the low signal of the polarization. And actually, having more data, using the isobar collision, actually, this is a little bit smaller colliding system compared to gold-gold, but a lot of statistics, so we do see much clearer signal for this elliptic flow-driven polarization. But as I mentioned, so there are initial fluctuation, density fluctuation. So in general, we have this kind of elliptical shape, but depending on the event, sometimes we do have this triangular-like initial geometry, then that causes the triangular flow. Then, similar to the elliptic flow, we do also expect this kind of the vorticity. And indeed, the data shows a similar pattern. So this clearly indicated that there is a triangular flow-driven polarization in this case. Yeah, let me say one more thing that, there have been the sign puzzle in this PZ measurement, meaning that many theoretical models that successfully describe the global polarization data fail to describe this sign of PZ measurement. So I list as much as possible, but for example, this hydro calculation shows the opposite sign of the compared to the data. But recently, including new a term called shear tensor seems to explain the data, but there is still debate how to implement this term. So that brings to my summary. So the observation of global polarization that indicate a vertical fluid really open new direction in the study of QCD matter and also the dynamics in heavy ion collision. I didn't have time to show many other results like a differential measurement. So actually there are still many open questions and we do not understand yet. So of course we need more precise data for better understanding the nature of the polarization and vorticity in heavy ion collision. And I will stop here, but just to mention that there are several other new ideas for kind of the exotic vertical structure like a vortex ring, and that can be studied in the future experiment or future data. Yeah, thank you so much.
Thank you very much for the nice presentation on the heavy ion polarization at heavy ion collision. So now, is there any question or comment? Too clear? Okay, could you go, yes, could you go back to the one page before?
Mm-hmm.
One more. Yes. Oh, this one is not. Oh, okay. Sorry.
Maybe one more.
Yeah. Some of the calculation and so, some of the inconsistency between that one. Could you give me a little bit more comment to what caused the difference?
In the calculation.
Yes.
In the model.
Yes.
Yeah, actually that is not well understood, I would say, because, for example, you see even the same type of the model, like a hydro model, but slightly different implementation and different initial condition, for example, that predicts different sign. So yeah, we still do not understand completely, but so that is discussion is ongoing.
I see. And what kind of the data will help to solve such kind of the discussion? So what is necessary for the future?
Right. So that is one of the motivation to look at this higher order one, and we do observe this higher order polarization, and yeah, we are waiting for example, this model can also explain that data, for example, by including this new term. Right.
I see. Such kind of new term, that one is coming from the some theoretical idea or some the empirical experiment want to introduce this kind of the terms. I'm not familiar, but
when I talked to one of the experts, he said they are somehow missing this term.
So still under discussion.
Yes.
Okay, thank you very much. So is there any other question or comment? We have 1 minute more. Okay, so let me thank again. Very nice talk. Okay, let me call the next speaker, Take Saito. Yes. He will talk about the studying of the hypernuclear with heavy ion beams, nuclear immersion, and machine learning. So, are you ready for the presentation? Yes, please.
So I need a slide coming back.
Yeah, now you're working on it.まだ出てないから多分コントロールできてない。Okay, now it's clear.
So thank you very much. So first of all, so I'd like to thank organizers for inviting me to this conference. So usually I'm talking about our hypernuclear project with heavy ion beams, but we also want to talk about the nuclear immersion this time and together with machine learning. So I just want to remind you for the hypernuclear heavy ion part that we are studying the hypernuclei by using the induced reaction of the heavy ion beam on the fixed target. So then we just produce a hypernuclei going to the forward direction, and we observe the hypernuclei in flight. So maybe I don't have to talk about this one in detail, but I just want to remind you that we had a pioneering experiment, so-called HiFi Phase 0, in 2009 at GSI. And we somehow initiated two puzzles in the hypernuclear physics field. One was the signal indicating the NN lambda bound state, and another one is the short lifetime of the hypertriton. So, and the hypertriton is the benchmark of the hypernuclear physics. And it was understood as the lambda is weakly bound to the deuterium core with the binding energy of only 130 keV. But so what we have observed was the shorter lifetime of the hypertriton, which is contradicting to this binding, weakly binding nature of the hypertriton. So, so the hypertriton lifetime is getting the hot topics in our field. So, for example, STAR was measuring also the hypertriton lifetime with heavy ion collisions. And the first they showed a short lifetime. And Alice also did the measurement and the first showing the short lifetime, somehow similar to our value. Then later, STAR comes to the shorter, but Alice comes to longer. and very recently, so STAR performed the fixed target experiment, and the lifetime becomes longer. So, so now this one is so-called hypertriton puzzles, or hypertriton lifetime puzzle, and we need precise measurement. Okay, here I just want to show the most recent publication from last month from the STAR. And they have somehow concluded that the hypertriton lifetime and also the hydrogen 4 lambda lifetime is considerably shorter or lower than the free lambda lifetime, but it is still not clear. And so what we want to provide is at least one data point with the very small errors. So this is what we really want to do. And so now also the hypertriton binding energy was revisited by the STAR collaboration, and it was published in the Nature Physics 2 years ago. And what is very interesting is that the hypertriton binding energy is significantly larger than the former value, which is 130 keV. But the error is rather large. So the statistical error and the systematical error is around 100 keV. So therefore, also for the binding energy, we need the one data point with the very small error bar. So this is what we want to try. So now I just want to show how we challenge the hypertriton lifetime. So we come to the idea to using the fragment separator at the GSI, which is usually used to study the rare isotope beams or exotic nuclei. So here I just magnify the fragment separator, and what we want to do is in the mid-focal plane of the FRS, and we want to produce the hypernuclei or NN lambda state if it exists by using the same reaction of the HiFi experiment. And then we want to measure pions in the mid-focal plane right after the production of the hypernuclei. And then those decay residues are transported to the second half of the fragment separator. The fragment separator is very well established, and the momentum resolving power is about 10 to minus 4. So this is 2 or 3 orders of magnitude better than the HiFi. So already we have a huge benefit. And what we want to try was also for the pion measurement, so we want to achieve the large acceptance and also the reasonable momentum resolving power for the pions. So this is what we tried. So since this project was rather new, so I just want to show some background of this project. So it was started with Christophe Laporte in 2012 at the GSI. And in the beginning, our idea was to use the 2 dipole magnet in the mid-focal plane. So then later in 2015, so we are lucky that the FAIR new star somehow defined that our experiment as the day 1 experiment of the new star. So in 2016, so we came to the idea to use the WASA detector in the mid-focal plane of the fragment separator. So what we tried was to mount or implement the WASA, which was in Jülich at that time, and putting into the mid-focal plane of the fragment separator. So then, so we submitted the proposal to the GSI PAC, and it was approved with the highest priority. And then from 2017 to 18, so we made the preparation for moving the WASA detector from Jülich to GSI. And then from 2019, we started the serious preparation at the GSI. So in 2019, I have some change in my affiliation. So I got a position at the weekend. So therefore, I can also put the Japanese contribution to this project. So it was rather good. And also we can, okay, so I kept also my group at GSI, and we could hire the permanent staff, a permanent engineering staff at the GSI working for this project. And also I got the additional position in China, so I could also put the Chinese contribution to this project. And it was happening in 2019. Then we already moved the WASA in 2019. And then since then, we start the serious preparation. And I just want to show 2 phases. They are stationed at the GSI and seriously working for the WASA also during the COVID-19. So he is Yoshiki Tanaka, who is the permanent researcher of my group at RIKEN, and he is Vasyl Drost, so from Ukraine. And he is my PhD student at my GSI group. And those two people are really working together with the local GSI staff to make the preparation of the WASA experiment. So then in 2020, so we had some difficulty for the COVID, but those two people are stationed at the GSI and continue the preparation. And then also at the meeting time, so the people at the RIKEN and the people in the Christoph's group in Spain, so we prepared the Monte Carlo simulation and analysis code, and then we investigated our performance. So this is not the experimental result, this is what we expect in the experiment of 4 days. So we are expecting that the peak is like this, and the accuracy of the lifetime is about 8 picoseconds. And we also prepared some machine learning model with GNN. And so this will be in detail discussed by Hiroyuki Ekawa tomorrow in the parallel session in this conference. So then we just performed our experiment. So we did 2 experiments. The first one was for the eta prime nucleus, and another one for the right hypernuclei. And then so I just want to talk about this experiment with right hypernuclei. And we also had some difficulty for the helium supply because the helium is coming from Russia. But we had, during our experiment, the war in the Ukraine was started. So therefore, we also have some difficulty, but we somehow could solve the problem and we could continue the experiment. Okay, so this is our apparatus. So this is the cesium iodide calorimeter surrounding the superconducting magnet, solenoid magnet. And inside of the superconducting solenoid magnet, so we have, and also surrounding the WASA detector, we have several detectors. I just want to show some scheme. So this is the superconducting solenoid magnet, and the cesium iodide calorimeter is surrounding. And also inside the conventional mini drift chamber of the WASA detector is mounted. And we also put lots of additional detectors and also the material. Okay, first, our target was the diamond with 3 centimeter thick, and it was provided by the Gifu University in Japan. And we built up the 5 fiber stations. And also we built up 1 mini fiber station inside of the ion yoke. And we also implemented the new time of flight barrel. Also, we developed the new end cap detectors. And then, so this is the photo of the WASA at the S2 on the mid-focal plane of the fragment separator. And then this is another photo of the end point of the fragment separator because we also have to measure the fragments, our decay residues from the hypernuclear decay. So these are the photos. So now, one of the aim of this experiment was to confirm if this NL lambda bound state or resonance state is existing or not in the HiFi. So we could not see the resonance state because we had a secondary vertex trigger, but with this experiment, we didn't have to use the secondary vertex trigger, so therefore we could also see the resonance. So here I'm just showing the paper which was presented by Professor Tam. And and also, this was somehow showing the possibility for the NL lambda resonance. But also the same collaboration had 2 different interpretations because the data is, somehow the statistics is not so high with this data. So therefore, in our experiments, we want to really confirm or see if this NL lambda exists or not. And we have already accumulated almost 200 million deuteron data at the end point of the fragment separator, and then so we are now performing the data analysis. So So we are now just starting the data analysis because the experiment was done in the end of March. So, but what we will see or conclude is the lifetime of the hypertriton and the hydrogen for lambda, also for the NL lambda state by looking into the deuterium plus pi minus final state. And also we made some challenge with the heavier projectile with, for seeing the hypertriton with different projectile. And we also took the data for the proton-rich hypernucleus boron 9 lambda. And also the detail of the data will be discussed by Hiroyuki Ekawa tomorrow. So this is the main part of the WASA collaboration. And here I just want to show some people working for our experiment. So this was just taken right after the experiment in February this year. And then I just want to show several phases emphasized. Okay, first, those 4 people, okay, these 2 people are stationed at the GSI, working together with our young engineers. And then we have also lots of people contributing to the WASA experiment. And they are from RIKEM, okay, from my group at RIKEM, and also Christoph's group in Spain. So I would say that these are now the phases for our hypernuclear project at the NuSTAR in FAIR. Okay, so now I come to the binding energy of the hypertriton. So what we do is the analysis of the JPAC EO7 nuclear emulsions. So this result was already discussed by Professor Nakazawa yesterday. So they have already found 33 double hypernuclear candidates, and some of them are identified and published. So, but in the non-triggered data, well, we don't know. Okay, these are sort of the discovered event with hybrid method, but there should be lots of hypernuclear events recorded in the emulsion because we put the K-on beams anyway there. And what we expect is that there should be 1,000 double-stranded hypernuclear events recorded in the 1,000 emulsion plate, and also millions of single-stranded hypernuclear events. And we can somehow discover all of the events when we do the overall scanning of all of the emulsion sheets. But this is not so easy. So now nuclear emulsion data is like this, so mainly their background. And the data size is also huge. So for example, when we scanned one emulsion sheet, the data size is about 100 terabytes. But most of them are just background. So then conventional method is that we take the data and we inspect by eyes. And if we do it with 10 people, and then it will take 560 years. And then, so we cannot wait for this years. So then, when I got the position at RIKEN in 2018, so since I was somehow a newcomer to Japan, so I was also thinking of what kind of contribution I can make also to the JPAC. And then I had a discussion with Professor Nakazawa, and then I have somehow started to analyze this nuclear emulsion with machine learning. So this is rather a new project since 2020. And then our goal is to see the millions of single-stranded hypernuclei and also the 1,000 double-stranded hypernuclear events. This is what we want to do. And then with machine learning, we can reduce this 560 years to 3 years. So this is what we are now doing. So now, okay, so we are already doing the new emulsion overall scanning at RIKEN in my laboratory. And there are already 3 stations operational for 2 years. And then I just got email today that 2 more stations just came to our group at RIKEN from Gifu University. And now we have a totally 5 stations. And we can also speed up the overall scanning. And we have already developed the machine learning model, so we can really do the physics. So, but for the machine learning, so I just want to emphasize that the most important for the machine learning development is the quantity and the quality of the training data. However, for the hypertriton search or for the double hypernuclei, we don't have no existing data for the training. So our way to make the training data was to do the Monte Carlo simulation and also making also the machine learning, using the machine learning technique for the image transfer. So we used the GAN technique, and we somehow simulated the training model, and then we make the development of the machine learning model. And we also decided to use the mask RCNN model, so we also developed the model for our hypernuclear event detections. And the detail will be talked by the Manami Nakagawa also tomorrow in the parallel session. And then so it was successful. And then in February last year, so we have already discovered the first hypertriton event in the nuclear immersion. And the first event was published in the Nature Reviews Physics. And then so this is the first event. So K minus beam is coming from somewhere, and they stopped here, and then producing the hypertriton with associated particles, and then it decays. And then so this discovery already guarantees that we can really measure the hypertriton binding energy very precisely, because we can discover many, many hypertritons. We have already discovered few tens of hypertriton already. And then we also somehow estimated or investigated how much precision we can achieve. And our estimated systematic uncertainty is about 28 kb, and it was also published by our student at EPJ. So this is the collaboration for the nuclear immersion. And then, so now I just want to come to the perspective. So with heavy ion beams, so we want to continue the WASA FRS-like experiment also at FAIR by using the super FRS. So for this project, so we have already started the upgrading of the WASA. So I got about €500,000 budget from Chinese government for upgrading the inner Jewish chamber inside of the WASA superconducting magnet, and it is ongoing. And we are also now trying to make the new magnet with the new superconducting material and also the electric cooler for the magnet. And we are also now starting to develop or consider the new detector putting into the mid-focal plane, and this is in progress. And with those devices, so what we can do is the continue of the single lambda hypernuclei, and so up to mass number 20, and we can measure the binding energy. We can also measure the lifetime, and we can also use the proton-rich projectile also to study the proton-rich hypernuclei, and we can also use the charge exchanging reaction also to study the neutral and the very neutron-rich hypernuclei. So another perspective is the new hypernuclear project at the higher facility in China, and where we want to produce hypernuclear at 4.25 GeV per nuclear heavy ion beams, and we can produce and identify the Xi and lambda hypernuclei, and we can measure the binding energy and also the lifetime. And also for the single hypernuclei, what I'm considering is to perform the scattering experiment, because the reconstruction rate of the single lambda hypernuclei with this experiment is very huge, so few millions per day. And then for this detector, so we can use to develop the technology for the super FRS and for the dipole magnet. So I'm considering to move the Aladdin magnet from GSI to China, because it is now available at GSI. So, and also for with the emulsions, we are going to develop, or actually we are already developing the detector or the machine learning model to detect the free body decay, to measure the binding energy of the hydrogen 4 lambda and helium 4 lambda, and also for the machine learning model to detect the double lambda hypernuclear events. So this is now ongoing. And this is complementary to our heavy ion project. to measure the lifetime and also to measure the magnetic moment and so on. So we want to do all of them together. So, okay, my time is over, but I just want to show two interesting discovery. So with the nuclear emulsion, so our machine learning model detects this kind of decay vertex. Okay, two-body decay back to back. This is pion, this is helium. So we identify that this is helium-4 and this is pi minus from the hydrogen-4 lambda. So we follow this hypernucleus and we observe that it is scattering. So it is scattered in one of the nucleus, in the nuclear emulsion, and then we also follow and coming to the reaction point. So what was happening was that, so beam interaction is happening there, and then the single lambda hypernucleus is produced, and running for a while, and scattered and decayed. So this we can really see visually in our nuclear emulsion data. Another one is again, so we again discover or observe this vertex with our machine learning model, and we identify pion and helium, and it is coming from hydrogen-4 lambda. So, okay, so here I just put it with expanded one. And then so hydrogen-4 lambda, so we follow. And what we observed was that it is coming from this kind of vertex. I magnify this part, and what was happening there is that Guzai minus is running and stopped, and here double lambda hypernucleus is produced, and then one of the decay residue is the hydrogen-4 lambda, and running and decay to helium-4 and pi minus. So this discovery somehow tells us that we are now searching for the single lambda hypernuclei. However, as a byproduct, we can also find some double hypernuclear production and decay. So this is what now we are doing very much. Okay, so then let me come to the summary. So the discussion which I was talking now is summarized in this paper. So I talked about the WASA, FRS. I also talked about our our effort for the nuclear emulsion with machine learning. And also I talked about some perspective at FAIR and also in China. So then finally I just want to show this photo. So my group at the weekend is rather new, so it was just established, well, I started from the scratch 3 years ago, but now it is somehow grown already about 20 people. And I just want to somehow advertise that Manami Nakagawa is talking about this nuclear emulsion and machine learning tomorrow in the parallel session, and Hiroyuki Ekawa will talk about the WASA-FRS. Thank you very much for your attention.
Okay. Thank you for the nice review on the wide variety of the talk about the recent progress of the hypernuclear physics. So, okay, Abraham, please.
When you conjectured the existence of lambda neutron-neutron system, a bound system that decays with a lifetime shorter than that of the hypertriton, than of the free lambda, it fitted into various measurements, all of which came with shorter lifetimes for the hypertriton than for the free lambda. But a very simple estimate that I made with collaborators in several papers or reviews shows, and I can repeat it here, that the lifetime one expects for lambda NN system is longer, and not by just little. It's longer by perhaps 30% or so than the free lambda lifetime. And we have no indications for such longer than free lambda lifetime. So would you comment on this?
Actually, we measured the lifetime of this NN lambda state, and it was 180 picosecond. So, but, well, I don't know. So I think our accuracy in the former measurement was not excellent. So I think we have to measure the lifetime and also the invariant mass anyway precisely with the current data set. So I cannot make any comment because we have not done the data analysis, but we do the analysis and let's see. So I don't know. So we have to do the analysis.
Okay, the host, please.
Tarek, that is really an impressive program which you have presented here, and covering almost all sectors of strangeness physics. But what is kind of missing, and which would be important for theory, I think, is also to look for the sigma hyperon. And is there any plan to have a dedicated experiment to look for sigma nucleus interactions?
Actually, so yes, we do. So for the sigma hypernucleus, so what we have already started to was to see if the sigma hypernucleus exists, or we can see if the sigma hypernucleus or not in the nuclear margin. So what we are trying to see is that first we can somehow see the sigma minus hyperon is stopped in the nuclear margin. This is very similar to Xi minus. So it has a sort of struggling. So we have to make the machine learning model to discover the sigma minus stopped. And then when sigma minus is absorbed in the nucleus, and by the strong interaction, this sometimes maybe it comes to the two nucleus back to back. And if we can see this, and this may be the indication of the sigma hypernucleus, so it is what we are trying to see. So maybe in the 1 or 2 years, so I think we can find some candidates if the sigma hypernucleus really exists in our data set.
I mean, you will certainly produce sigmas as well, even though you haven't yet. Okay.
Okay. Just to finishing, before the finishing, I would like to have the very short comment about your comment about J-lambda and lambda. So the two papers we published, and you said that the interpretation is different, but actually interpretation is the same. The way of the presentation for what we see, that one is no clear peak, and the way of the presentation is different, but the interpretation is the same. So there is no significant peak. So
yeah, but you give a sort of a defined impression anyway to the readers.
That impression,
and at least I got the defined impression.
Okay,
so this is my observation.
Okay, but if you see it carefully, the interpretation is the same.
Okay.
So the way of the presentation may be different.
Okay.
Okay. Let's thank again.
Yeah, thank you very much.
Okay, let me call the next speaker. Koji Miwa. He will talk about the recent progress and the future prospect of the hypernuclear scattering experiment. So actually, you have 20 minutes plus 5, so there is some time, but that one is 20 minutes, so in total, you have 25 minutes. Okay, please start.
Thank you, Chairman. So it is my great honor to have a chance to present our activities. So my title is Recent Progress and the Future Prospect of Hyperon-Nucleon Scattering Experiment. I'm Koji Miwa, Tohoku University. So I'm going to talk on behalf of the E40 and the P686 collaborations. So this is my content. So after a brief introduction, so I want to summarize the sigma proton scattering experiment. So we succeeded in measuring the sigma minus proton and the sigma plus proton differential cross-section. And for the sigma plus proton case, so we try to derive the phase shift of this sigma plus proton channel. And then we want to move to the future prospect, lambda proton scattering with polarized lambda beam. And I want to come to summary. So as you know, the realistic nucleon-nucleon potentials such as the CD bond, F18, and the Nijmegen NN interaction have been established. And in developing these theories, a lot of NN scattering data were used. And now this realistic interaction is making a solid base of the nuclear studies. Then now three-body nuclear force was established from the PD scattering. And this interaction is necessary to understand the nuclear binding energy and also the equation of state of nuclear matter. So this is a NN interaction, but baryon-baryon interaction situation is very different. So we have boson exchange model like the Nijmegen, or Coke-based model like a Coke cluster model, and the recent chiral EFT extended to the hyperonucleon sector. But the experimental data to constrain these theories are extremely scarce. So we need good quality two-body scattering data to feedback these theories, and also to test theories, including the lattice QCD. So the first step to realize the accurate hyperon nucleon scattering experiment was this sigma proton scattering. So we measure the differential cross-section of the sigma proton channels. So the physics motivation, one of the biggest physics motivation is the verification of the quark-Pauli repulsion. So in the sigma plus proton channel with spin 1 system, this contains a up quark pair having the same spin and color. And this Pauli-Forbidden channel in quark level make this potential very repulsive. So we want to verify this repulsive nature from the scattering experiment. And also, we want to put constraints on the baryon-baryon interaction theories. So this is some theoretical calculation of the sigma plus proton differential cross-section. And the theoretical prediction is very different depending on the theoretical model. So by providing the good quality data, so we want to put constraint to theories. Then we measured this systematic measurement of the sigma proton channels, sigma plus proton and the sigma minus proton elastic scattering, and also the lambda n conversion channel. And also in this sigma plus proton channel, so we measured, derived the phase shift value for the first time to compare theory directly. Okay, so I want to move to our experiment and our experimental concept. So we measure two successive two-body reaction. And the first one is this sigma production inside the liquid hydrogen target. And this sigma production was targeted by this beamline and forward spectrometers. And from the missing mass, so we can identify the production of the sigma. Then sigma particle running inside the liquid hydrogen target sometimes happens a reaction, and such reacted events were detected by the surrounding detector system called catch system. So as we said, the sigma particle running inside the liquid hydrogen target is regarded as a sigma beam in this our experiment. And to identify this sigma beam, so at first we identify the K plus production at the forward spectrometer like this. Then we calculate the missing mass spectrum, so we can clearly identify the sigma production. Then from the missing momentum, we can identify the sigma momentum event by event. Then momentum, sigma beam momentum range is from typically 0.4 GeV to 0.8 GeV over C. And sometimes this running sigma hyperon interact with a proton inside the liquid hydrogen target, and we try to identify these reaction event with this catch system. And for the particle identification, so we use this energy deposit at this fiber tracking detector, and also the total energy deposit in the VGO calorimeters. Then by using making this so-called delta EE plot, fiber energy deposit and the VGO total energy deposit, so we can clearly see proton and pion lines. And in the sigma minus proton channel case, so this proton in coincidence with the sigma production is a clear sign of secondary reaction, because the sigma minus does not decay to the proton. So this proton means there is some secondary reaction. But many of these secondary reactions come from the neutron-proton scattering from the sigma minus decay. So sigma minus decay to the neutron and the pi minus, and this neutron knock out the proton. So this makes the main background of the sigma proton scattering. But this is also the good channel to understand our systematics of the differential cross-section measurement. And this red point shows the measured neutron-proton differential cross-sections. So from this measurement, so the derived differential cross-section of the neutron-proton scattering are very reasonable. So our measurement looks okay. Then, so we want to identify the sigma proton scattering event. So we compare the kinematical relation between the recoil angle and the kinetic energy of the recoil proton. So we define two kinetic energies. One is actually measured kinetic energy of the recoiled proton, and the second one is a calculated energy from this recoiled angle, assuming the sigma proton elastic scattering kinematics. Then we take this difference. Then in the typical example, so we can see the peak corresponding to the sigma minus proton scattering event at this delta E value equals 0. Then, and if we change the assumption here, for example, sigma minus proton to lambda n conversion assumption, so we can see clear sigma minus p to lambda n conversion interaction like this. Then finally, we can derive the differential cross-section like this. And this is a sigma minus proton elastic scattering, and this is a sigma minus p to lambda n in elastic scattering. So we realize a very improved cross-section data, and typical accuracy is 10% with a much narrower angular step of d cosine theta equals 0.1. And now we can see clear angular dependence. So sigma minus proton case, it is a very forward angular distribution as a prediction by the theories. And lambda n conversion case, the angular distribution becomes rather moderate. Okay, and these blue lines and also yellow and this red line, these are FFF2 Quark model prediction and the chiral EFT prediction. These predictions show a reasonable angular dependence, but Nijmegen model, this magenta lines clearly underestimate the forward angle. Okay, so we want to go to the sigma plus proton scattering case. So in this channel, so the related to the Pauli effect in quark level, so this channel is very interesting, important. So if the more repulsive, the more repulsive potential in triplet S1 channel is, the larger differential cross-section is predicted, like this FFF2 quark model, this blue lines. But from our experimental results, so we found the differential cross-section is much smaller than FFF2 prediction and also previous KK measurements. Okay, so this is a comparison of theories. So as I said, the FFF2 and FFF quark cluster model are too large compared to the data. And for the chiral EFT model, this red and orange lines, so the momentum dependence does not match with data. So at a higher momentum, the cross-section becomes larger. And the Nijmegen model are rather consistent, but actually this NSC 97F, so this model predicts attractive sigma n interaction. So this is not realistic, I think. Okay, then additionally, we perform the phase shift analysis. So the sigma plus proton isospin 3-house channel, so this is a very special channel because this is simply described by the 27 plate and also 10 plate. And this 27 plate is same multiplate in NN isospin 1 channel. So this multiplate is constrained from this PP NN isospin 1 channel, and the theoretical uncertainty might be small. So this is a theoretical calculation of the phase shift value. So it looks like the similar trend of the NN isospin 1 channel. So we try to do the phase shift analysis. So we set two parameters, this triplet S1 channel phase shift and singlet P1 phase shift. This included in template. So these two parameters should be determined from the fixed fitting, but the other phase shift value up to D wave were fixed on the some theories or PP scattering phase shift value. Then we obtain this kind of the momentum dependence of the phase shift value. So the point shows the difference of the used this difference of the used fixed phase shift value, but there's a little difference between these points, and it shows a momentum dependence from the minus 20 degree to minus 30 degree. So derived phase shift suggests that triplet S1 interaction is moderately repulsive. Okay, so I want to go to the lambda proton scattering. So in the sigma particle case, so the sigma hyperon is merely bound in the nucleus, but in the lambda case, so the situation is completely different. So reliable lambda n two-body interaction is a key to deepen the hypernuclear physics and also the neutron star physics, and especially we want to reveal the lambda n three-body interaction based on this realistic lambda n two-body interaction. And recently, so we have many accurate two-body new data from the femtoscopy, from heavier collision experiment, and class experiment. And this time we want to show our new project to measure lambda proton scattering with polarized lambda beam. Today, I want to show the feasibility of this experiment using the current E40 data, and we want to show expected result in new experiment. So the issue, experimental issue to be solved is how to identify the lambda production from the hydrogen target. So we have to establish the pi minus proton K0 lambda reaction. So in this case, we identify the pi plus in the forward spectrometer, and the pi minus was identified using surrounding the detector system catch. So this is a byproduct data of the E40. Then we can identify lambda clearly like this. So by using this lambda particle, we can do the analysis of the scattering. So the one advantage of this lambda production is its very high spin polarization. So from the past experiment in this reaction, so lambda spin is highly polarized, reported from the very old data with respect to the production plane. And by using our E40 data, we confirmed its high polarization of lambda particle. So this is presented by Sakao-san. Okay. Then we also try to identify the scattering, lambda p scattering event from the current about 10 to the 4th lambda beam. And we identified this kind of the kinematically consistent event for this recoil proton peak here, and for the scattered lambda peak here. So this experiment looks very feasible. And this experiment is also closely related to our future project, Hadron Hall extension project. And this is one of the flagship experiments at this K1.1 beamline. So this will be reported in detail by Sakuma-san in last day. Okay, so we are going to perform the lambda proton scattering experiment. We use a similar setup using the so-called catch system like this. And this high polarization, spin high polarization nature of lambda beam enable us to measure not only the differential cross-section, but also the spin observable, like the analyzing power of the lambda analyzing power, and also the lambda depolarization. So this is our expected result. So this is expectation of the differential cross-section, analyzing power, and the depolarization. So now there's no differential observable of lambda p scattering so far. So we have integrated cross-section information, but there's no differential cross-section data. So if you see the theories, the angular dependence is completely different. So by providing the very good quality data, so we want to put constraint on theories. And also situation is same for the spin observable. So especially the sigma n threshold region, the spin observable theoretical calculation is completely model dependent. So by providing typically 10% accuracy data, we want to put these constraints to theories. Then these new data becomes essential constraint to determine the spin-dependent lambda n interaction. So I want to summarize my talk. So baryon-baryon interaction are important. It should be the basic of the hypernuclear physics. And now hyperon-nucleon scattering experiment gets possible. And we successfully realize a systematic measurement of the sigma proton scattering at J-Park. And we provided very improved differential cross-section. And also we derived the phasicist value of the sigma plus proton triplet S1 channel. And we are going to perform the differential cross-section and the spin observable measurement of the lambda proton scattering with polarized lambda beam. So we hope our data become important input to improve theoretical models. Thank you very much.
Yes, thank you for the nice review on the recent progress and the future prospects of the Hyperion nuclear scattering experiment. So, Laura, please.
So, congratulations, fantastic talk and fantastic results. Can you go to slide 28?
28?
28, where you show the cross sections for sigma plus proton. Yeah, so in the panel where you have the momentum, 750, 850 MeV of C, there is a bump. I didn't understand what this bump is. If you could just explain.
You mean here?
Yes, this...
from the data point, we can see clearly enhancement over here, but to be honest, the statistics is not so enough. So to say more conclusive, results, so we need more statistics.
Okay, I see. And then I had another question. So you are now showing results with a minimum momentum of 470 MeV over C. What is the minimum that you can reach in terms of momentum for your next measurement? The minimum sigma momentum? Yes, the smallest that you will be able to measure.
By using the pi-k reaction, so available minimum momentum might be 0.4 or something. So,
thank you very much.
Yeah, if we increase the beam momentum, so we can decrease the momentum at a 0 degree forward angular region, but available minimum momentum might be 0.4 or less. Thank you very much.
Okay, any other question? Yes, host.
I'm really impressed what you have already done and what you will do. And I think it's very important for theory indeed. In particular, if you would have angular distributions, not only at one energy, but at certain energies, that would further help to constrain the theoretical input and distinguish between the different models. You have shown, at the polarization data and the comparison to the models, that there's a big uncertainty apparently on the spin interactions, for example. And so that was, right. So it's a severe deficiency of the theory until now. I would say that these predictions for the polarization, for the analyzing powers are so much different and fluctuating arbitrarily almost around the data. So that shows that this type of experiment is really crucial for the further progress of theoretical work.
Yeah, and especially so this momentum, around 0.6 J over C. So this is correspond to the sigma n threshold region. So the theoretical model is very different at this energy region. So we want to measure these kinds of the analyzing power to constrain the theories.
And for hypernuclear structure, this low energy behavior, that is a particular important part of the input.
Yeah, thank you very much.
Okay, so it's now time. So let's thank again.
Thank you very much.
Okay, let me call the last speaker of this session, Nick Zahario. And he will talk about the study of the hypernuclear interaction using the class detector.
All right, so let me start by expressing my gratitude for this wonderful opportunity to be here. As the title says, today I'll give you an experimental overview of study of the hypernuclear interaction utilizing exclusive Hyperon photoproduction reactions with the CBAV large acceptance spectrometer. I'll start my talk with a brief motivation, and then I'll go over a brief introduction of the experimental setup that we utilize at JLab, where I introduced the CBAV large acceptance spectrometer. And then I'll discuss the ongoing efforts in studying the hypernuclear interaction via exclusive Hyperon photoproduction processes, where I'll show some of our recent results on the elastic lambda p cross-section determination, as well as some of our upcoming results, both on sigma minus p elastic and lambda d, with the latter here being one of the main focus to probe these three-body forces. And before I conclude, I will also introduce how we can utilize a large set of polarization observables to obtain further constraints on the underlying dynamics. All right, so understanding both the nuclear-nuclear interaction and the hypernuclear interaction is actually crucial, is critical in order to obtain a complete picture of the strong interaction. And we know over the past several decades, the nuclear-nuclear interaction has been extensively studied, is well understood. However, very little is known in the interaction that involves other members of the octet, namely the hyperons. Now, obtaining a detailed understanding of the hypernuclear interaction will allow us to better understand the properties and composition of neutron stars. It will allow us to understand hypernuclear structure and hyperon matter. And in the more general sense, it will allow us to extend the nuclear-nuclear interaction into a more unified picture that is demanded by SU3 symmetry. Now, as we've heard today, hyperons, of course, are expected to appear within the core of neutron star in the core of neutron stars at densities of about 2 to 3 times the nuclear saturation density. But the main issue here is that the appearance of hyperons actually soften the equation of state of neutron star, which leads to a significant reduction in the maximum allowed mass that is incompatible with recent experimental observations. And this is exactly what we refer to as the hyperon puzzle. In the past several decades, there's been a lot of theoretical efforts in order to provide possible solutions. Some of these solutions were discussed today, lying within kind of repulsive two-body and three-body forces that stiffen the equation of state, bringing it back to the maximum calculated mass to be consistent with recent observations. Now, the main problem here lies in the fact that the hyperon nuclear interaction is poorly constrained. In fact, currently, well, until recently, there was only 1,300 data points dating back from 1970 from bubble chambers experiments. And this kind of reflected in the large uncertainties in the determined scattering length. And of course, this is reflected with this is due to the fact that it's extremely difficult performing high precision scattering experiments with hyperon beams that decay very fast. And there is, of course, a clear need for experimental data in order to constrain the underlying dynamics of this reaction. And because of this, we put effort in so-called complementary approaches in order to, in an attempt to study this in an alternative way. Some of these approaches we've heard a lot over this conference, and we'll hear more in the upcoming days, is focused on hypernuclear studies, which do provide us invaluable information. However, these kind of studies do not give a direct access on the bare two-body hypernuclear interaction, and they're typically associated with systematics that are related to both medium modification as well as many-body effects. Now, today I'll be talking about another complementary approach that we utilize at JLab, utilizing final state interactions and two-step processes in hyperon photoproduction reaction to obtain more information. In fact, at JLab we use these two-step processes where a photoproduced hyperon undergoes a secondary rescattering either within the same target cell or within the same nucleus. The identification of the kaon here in the final state allows us to tag the hyperon beam, of course assuming that we have a tagged photon beam, and a hermetic detector allows us to fully reconstruct the reaction of the event by identifying the decay products of the hyperon as well as the rescattered nucleon. And in this kind of experiments, again, we can use both hydrogen and deuterium targets to study both lambda p and lambda n, or sigma p and sigma n. And today I'll be talking about some of the recent publication on lambda p and the ongoing works on sigma minus p and lambda d, focused on determination of cross-section, as well as a large set of polarization observables. Now, the experiment was performed at Thomas Jefferson Laboratory utilizing this 6 GeV era of the accelerator. You can see an aerial picture of the CPAF accelerator here, composed of 2 linacs, allowing the acceleration of electrons up to 6 GeV, providing a highly polarized electron beam of the order of 86% and high currents. The CPAF was able to deliver this high-quality beam at 3 experimental halls, this A, B, and C, for simultaneous and complementary experiments. Now, since then, this accelerator has been upgraded to deliver beams up to 12 GeV, and an additional hall D here was constructed for photo production experiments at 12 GeV, and we'll hear more about that in the upcoming days. Now, hall B houses the CPAF large acceptance spectrometer, housed the CPAF large acceptance spectrometer, which is a magnetic spectrometer that's built around a toroidal magnetic field. It's composed of several detector subsystems, including 3 regions of drift chambers for momentum determination, time of flight system, Cherenkov star counter. And the key here is that it provided us with an efficient detection of charged particles over a large fraction of the full solid angle. And this is a characteristic that is quite critical for the success of these kind of studies. Now, hall B also housed the target spectrometer, which allows the tagged photo production experiments just by identifying the electron that generated the Bremsstrahlung photon with a series of scintillators. Now, the first study I want to focus on is the results on the lambda p elastic scattering. This was the results that were published last year. In this study, we utilized, again, a tagged photon beam, lambda hyperon photo production on a proton target. We had a liquid deuterium target, 40 centimeter long. The hyperon here, we looked at events where the hyperon underwent secondary scattering within the proton, within the same target cell, generating the final state of interest, detecting the scattered proton as well as the decay products of the hyperon. In this case, we utilized the p pi minus branching. The reaction was reconstructed through an invariant mass technique on the p pi minus to identify the scattered hyperon. We're also able to employ missing mass techniques using information from the scattered proton, as well as an assumption about the target proton, reconstructing in this way the hyperon beam, this lambda before it rescatters with a missing mass technique. While the background was well understood using the missing mass technique and reconstructing the kaon that comes from the first vertex, again through missing mass techniques. Now, just like any other cross-section determination, this kind of approach, this determination of cross-sections are quite challenging. It requires a detailed knowledge of both detector acceptance and detector efficiency. These are characteristics that are typically established from realistic simulations as well as high statistic channels for detector efficiency. But more crucially, we needed to better understand well and determine accurately the luminosity of the hyperon beam, which of this L factor here, which of course depends on the hyperon beam momentum. The hyperon luminosity depends, of course, on the incident hyperon flux, which is proportional to the photoproduction cross-section that is well known, and it was determined, again, using class data. However, also this luminosity also depends on the average path length that the hyperons see within the target cell. And this is critical because all hyperons can be generated at all different angles. So it's not as straightforward. And in order to determine this, we used realistic simulations that account for beam size effects, as well as the kinematic dependence of the photoproduction cross-section, and even more crucially, the decay path of the hyperons, especially since a big portion of hyperons can decay well within the target cell. Now, the exclusivity of the reaction gave us a very good handle on background contributions. I won't go into the details here, but some of the backgrounds that we were able to establish were coming from the PP elastic scattering, with the proton coming from the lambda decay. There were some contributions from the 2 pion photoproduction, as well as the K plus sigma 0 channel. And these kind of contributions were able to we're able to minimize them with simple kinematical cuts. So here I'm showing our published result from class on the total differential cross-section as a function of the hyperon momentum. The class data are shown with the blue dots covering momenta between 0.9 and 2 GeV over C. You can see that our results compare quite well with the available world data, especially at lower hyperon momenta. At higher hyperon momenta, there seems to be a systematic shift to lower values, and we believe that this is due to the fact that earlier determinations were not accounting properly for background contributions, namely from this PP elastic scattering. Our data seem to agree well with the nitrogen potential at lower momenta, where they seem to also converge with predictions with the Jülich potential at higher hyperon momenta. And there's also a recent calculation done by Heidenbauer using a next to leading order chiral effective field theory, with the band here showing the uncertainty in the calculation, and our data agrees well with those measurements. Now, we're able to perform a study determining the PP inelastic scattering cross-section, PP to d pi plus, and we utilize this approach as a way to confirm our methodology to determine the differential cross-section. And in this, we utilized a pion photoproduction reaction where the nucleon underwent secondary rescattering and to produce the final state deuteron and the pion. And you can see the preliminary results from class. These are the red dots, and how they compare with the precise world data. They compare extremely well. They agree very well with statistical uncertainties from class data being of the size of the market, so quite small. And we expect that these results will have systematic uncertainties of the order of 10%. So this gives further confidence in the approach that we utilize. Now, just to switch quickly gears, we have a large program in studying other different channels. Here, briefly would like to discuss the sigma minus P elastic scattering cross-section. For this reaction, we utilize a photoproduction of lambda 1405, which decays into a sigma and a pion. And then we look at the events where the sigma undergoes scattering within the same target cell. We expect to have about 4,000 or 5,000 sigma minus P elastic scattering events. We heard just before the really nice study done by Jay Park, where they determined the differential cross-sections, and we expect to have a quite nice overlap with the results from Jay Park from about 0.6 GeV over C, while extending the kinematic coverage up to, I think, about 2 GeV over C. There's also ongoing efforts by collaborators at University of South Carolina looking at studying these 3 body forces through the determination of the elastic scattering cross-section of lambda d. In this experiment, we utilize a liquid deuterium target, 40 centimeters long, and we had a quick preliminary look at the data, and we expect to have about 4,000 lambda d elastic scattering, covering momenta from about 0.7 GeV all the way up to 1.4, 1.5 GeV, and a large fraction of the angles. We should expect to have preliminary results by the end of the year, early next year, so stay tuned for that. Now, quickly, I would like to briefly talk about polarization observables in these reactions. And in fact, because we are using for production reaction, we have access to a large set of polarization observables, specifically this sigma, B-spin asymmetry sigma, tau, OX, and OZ that are accessible utilizing a linearly polarized photon beam, as well as CX, CZ that are accessible using a circularly polarized photon beam. And the nice thing here is that we can utilize the fact that hyperons are self-analyzing, meaning that we can directly determine the polarization of the hyperon in the final state just by studying the angular dependence of its decay products. And in fact, for this two-step processes where the lambda undergoes secondary rescattering, we expect to have kind of a predicted effect on these polarization observables, and we can utilize that to place further constraints on the underlying dynamics. In fact, there's been a large set of predictions from theories, and I'm showing here some of the old predictions done from Miyakawa, focusing on lambda n final state interactions utilizing a deuterium target. In fact, in this calculation, they used two potentials, this NSC97F and NSC89, both of which gave the correct hypertritium binding energy. But as you can see from these predictions, both of these potentials can lead to very different predictions for polarization observables as specific kinematics. So this is kind of critical in how we can use these polarization observables to place further constraints. Now, due to the sake of time, I just want to focus on one of the observables, namely the beam spin asymmetry sigma here, which causes a cosine to phi modulation in the azimuthal distribution of the final state product that we're interested in, and this can be determined either for the kaon, for the lambda, or for the nucleon. For this study, I'm focusing on the lambda n process, where a photoproduced hyperon on the proton undergoes secondary rescattering with the spectator neutron within the same nucleus. For this kind of process, we have contributions from four mechanisms. Of course, the quasi-free reaction, which kind of dominates the cross-section, as well as from a pion-mediated reaction, lambda n rescattering, which we want to focus on, as well as k n rescattering contributions. And the beauty of this for this observable is that we can directly determine contributions, relative contributions from these various final state interactions based on this beam-spin asymmetry, on the dilutions of the beam-spin asymmetry as compared to the quasi-free. Now, for the quasi-free reaction, this kaon and the lambda, they go back to back in the center of mass, so one expects to have the same beam-spin asymmetry of both the kaon and the lambda, whereas for final state interactions, the dilution of the specific particle that we're looking at tends to be much more if it underwent that specific reaction. This was also looked at briefly for the sigma minus p scattering, I guess, from the same data set. And again, without going into the details, this is ongoing work. There's a lot to be done, but just to quickly highlight that these different reaction mechanisms can cause very unique combinations in the relative ratios of the beam-spin asymmetry, and we can use these to not only disentangle the various FSI mechanisms, but also select kinematic regimes where the lambda n interaction is dominated, and look for other polarization observables that can help us place constraints on the underlying dynamics. Now, before I conclude, I would like to talk briefly about what's coming up at Jefferson Lab. In fact, with 12 GeV era, we had a proposal that was submitted and approved. We expect to have this K-Long facility to go online in 2025. We'll utilize the detector that is housed in Hall D, this GlueX detector, which again is a 4-pi detector system, while upgrading the beamline components that will allow us for a K-Long experiments to be performed. In fact, we plan to utilize a compact photon source that will give us a 6 order of magnitude higher photon luminosity than previously achieved. This photon beam will be incident on a beryllium target, generating phi mesons that decay into K-longs, and then we utilize the K-longs that have a 3 orders of magnitude higher cross-section for hyperon forward production to study lambda and interaction. And you can see here our projections with the magenta and how they will compare with world data. Quite precise measurements, allowing both total as well as differential cross-sections to be performed. And more crucially, we expect to have the first ever access to study the elastic scattering of cascade and interaction. And with that, I want to quickly summarize. Today we've seen that how we can use exclusive Hyperon photoproduction reactions to study Hyperon nuclear interaction. These kind of reactions give access to both the cross-section as well as a large set of polarization observables. We talked about the first results from class on the lambda p elastic that were published last year. There's ongoing efforts on the sigma minus p elastic scattering as well as the lambda d. And there's also ongoing efforts on the determination of a large set of polarization observables that can place additional constraints. And of course, there's a lot of exciting results in the pipeline, so stay tuned for new results coming up from JLab. And with that, I'll like to conclude.
Thank you very much. The comprehensive, nice review on the class results. So now the question or comment, please. Yes, please.
So thank you very much for very beautiful data. Can you show angular distribution of lambda p scattering?
So we are currently, the results that we've determined for the total cross-sections, they're a little bit limited on statistics, but we're planning on utilizing a data mining aspect where we can group together data from other experiments and using a deuterium target. And there we're going to enhance our statistics tenfold and we'll be able to extract differential cross-section.
Okay, thank you. May another question?
Yes, please.
In your last part, you talked about cascading scattering. And how many cascade particles do you expect?
So actually for these type of experiments, this is proposed. So whatever I say, it's coming from simulations. There's a lot of assumptions that go into. For this study, if I recall correctly, we expect to have about 5,000 to 6,000 cascade and interactions.
Scattering events, okay.
Yes.
Yeah, so many, okay,
yeah.
Thank you.
It's quite a high statistic data set.
Okay, any other question or comment? Yes, Miwa-san.
Thank you very much for telling us recent progress. And for the sigma minus proton scattering case, so maybe I think so by changing the polarity of the pion, so you can also detect the sigma plus proton case. But in principle, so it's maybe suffer from the decay proton with this only one proton tagging. So could you tell us the perspective of this sigma plus proton channel?
Yes, so that's also in our pipeline. Our main problem right now is that we lack of manpower to look at this. We have so many things ongoing, and there's so many things we can do with these data sets, right? In fact, we also plan to, for this kind of, for the sigma minus P, we also plan to utilize a deuterium target where the sigma minus is generated on a neutron with a proton spectrator, right? So that it will not rely on the photo production of the lambda 1405. So we expect to have a little bit higher statistics. But yeah, the sigma plus P is also on the pipeline. We just need to have somebody, some manpower to look at this data set.
I see. Thank you very much.
Okay. Any other question or comment? Yes, please.
I have a question. You are able to go also to, let's say, lower energies? Because, let's say, these data you presented, let's say, some of them, they are already on the verge even for validity of Carl EFT.
Indeed.
So it's...
That is a problem we have with class, and the problem here relies with the fact that it's a magnetic spectrometer. And we require, for the reconstruction of charged particles, we can only reconstruct them if they have moment above 200, 300 MeV. That kind of limits our momentum coverage.
Thank you.
Okay. Any other question or comment? No? Okay. Thank you very much, Nick. Then let's thank also again for all speakers in this session. So organizer, do you have any comment? No, just lunch? Okay.
yes, they can see. They can see.
Can you hear me? Yeah. Okay, it's time. I think we should start. So welcome. Hello. You could take a seat. Welcome to this session, this afternoon session. We have a relatively short session before the poster session, just 4 talks. Before starting, let me remind people who are attending the conference online that they can ask questions. They can write the questions so through the chat or wherever, and then the people in charge will speak your questions. And so we have 4 talks, as I said, one of heavy ion collisions and production of nuclei and hypernuclei, 2 of lattice QCD, and the last one will be about effective field theory, pionless effective field theory.
Yes.
So we should start with Vodvina, Alexander Vodvina from Frankfurt. And yeah, you are here. Okay, you have 20 minutes in total. So in principle, you have 15 plus 5. So
do you hear me? Do you see my slides? It's okay, yes?
We hear you.
I hope. Yes?
Yes, we hear you.
Yes, thank you very much. So my talk is about production of nuclei and hypernuclei in relativistic ion collisions. You know, this is actually many body process, and usually there are no dominating channels. So this is the theory description, usually subdivided into main stages: dynamical stage leading to production of baryons, hyperons, and equilibrated nuclear system, and statistical decay of these excited nuclear systems. Then this is qualitative picture of the how dynamical, what we expect after dynamical stage. We have production, a lot of new baryons, spectator residues, and fragments and hyperfragments can be reduced from all these parts. For the description of the reduction, we use, for example, URPMD model and other model which is available, other transport models. And I do not describe there in details there. This is these are very well known models, and the same for statistical multifragmentation. How dynamical models works, they predict a lot of lambda hyperon, for example, in central collision, for example. This is peaked in mid rapidity region, but however, a lot of hyperon can be reduced in target and projectile region, and they can be captured and reduce hypernuclear and target in trajectile region also. In the moment when we connected with statistical models, this is for target and trajectile region, we have excited nuclear system, and usually we use statistical models to describe decay of the system at low excitation energy with evaporation efficient. At high excitation energy, we introduce new conception. This is statistical result volume with multifragmentation reactions. One of the model which use this new conception, this is a statistical multifragmentation model. Each include both compound nuclear process and smooth the transition to the result volume configurations. And finally, secondary the excitation of all these fragments. Then this is a general scheme how this fragment and hyperfragment can be reduced at first dynamical stage, then reduced lambda Guide captured by nuclear residue in projectile and target spectator, then starting point for statistical model, and final nuclear reduced after disintegration of the excited fragment. This is general scheme, but however, there was long tradition studying for fragment reduction in heavy ion collisions. Usually, it is subdivided into parts. First part, this is exactly projectile and target region spectator, which characterized so-called power law distribution of the reduced fragments. Another part, this is central collisions, which characterized by the exponential fall of the fragments. Sometimes people think that this is two different phenomena. However, I will show in this talk that it's very similar phenomena and can be described in the same procedure. This is again in spectator fragmentation region, fragmentation of relativistic projectile. You see this is a comparison with experimental data obtained in these reactions. The EOS calibration, this is qualitatively comparison, but this is very good. However, if we want to compare more quantitatively, we take Aladdin data obtained in GSI, and we really got very good description of the data. Very good description of the data obtained, and the main idea that the excitation energy of the spectator sources, excited statistical spectator sources, is not very high, not larger about than 10 MeV per nuclei, with corresponding temperature 6-8 MeV. So this is not very high energies. This is an example that in spectator region we can very good describe.
I think we should start.
You see what problem? You see me? You hear me?
Take a seat.
Yes, we hear you. Yeah.
Welcome to this session, this afternoon session. We have a relatively short session before the session, just for talks.
Okay,
Before
there is
starting,
someone on the Zoom.
Sorry, there is some.
In the conference online that they can ask questions. They can use. They can write the questions.
What is
it? To the chat or
what
whatever,
happened?
and then people in charge will.
So there is someone connected online who's
And
speaking.
We have four talks, as I said. One of heavy ion collisions and production of nuclei and hypernuclei, two of lattice QCD.
Yes.
So we should start with.
I am sorry, I have started some time ago.
From Frankfurt, and yeah, you are here. Okay, you have 20 minutes in total. So in principle, you have 15 plus 5.
I do not understand. I have started already or not?
You see my slide? It's okay, yes?
We hear you.
Okay.
I hope.
So this is me talking at the beginning of the session, right?
May I ask you, you have
Yeah.
opened the window with the stream.
My talk is about production of nuclei and hypernuclei in relativistic ion collisions. You know, this is actually my.
Víme, je to, on má spuštěný stream ještě na pozadí. No, ale to jsem mu říkal.
Please, yes. Tell them.
Mr. Botwina, you have opened the stream.
What happens?
So, excuse me.
Please open my slide.
Yes, okay.
Statistical decay of this excited nuclear system.
Okay, just.
Then this is qualitative picture of the how dynamical.
Mr. Botwina, can you hear us, please?
Hello.
Excuse me, I do not.
Okay.
That's the problem.
Do you hear me now? Do you see me or not?
We see you, we hear you, but you can't talk and simultaneously listen talks from the morning. That's the problem.
Okay.
Switch on, switch off slide you.
Yeah, we close
That's it. Thank you.
Okay. You can
Now
continue.
you hear me. I'm sorry. This is we have lost a lot of information. Okay, I will start around central collisions now. Formation of baryon cluster can also receive not from target and projectile residue, but from nucleon used in the mid-rapidity region. To understand this, we need look at the central collisions. So in central collisions, we produce very compressed baryon, which then expand to the sum result density, and afterward they interact this baryon between ourselves and reduce fragment. The idea to consider this result density and divide nuclear matter into clusters in chemical equilibrium and apply, for example, SMM to describe formation of these clusters. Then we check this mechanism with controlled models. We have for example, phase space generation for nucleon and hydrodynamical like generation, selected primary cluster by using coalescence mode like model, and statistical decay of this excited cluster. Just to show you what we have in the result, this is primary excited nuclear cluster after in nickel plus nickel system at 10 MeV, this at 100 MeV system, and after the decay, they turn out in this mass distribution of this primary cluster decay. So, and in this way, we were able to describe the latest experimental data obtained for the collaboration. Nobody have tried it consistently before in central collisions. This is nickel plus nickel system, gold plus gold system at low energy. So the description actually very good. And kinetic, and in the same time, we describe kinetic of fragment in these reactions. Also, nobody has done it before. And also, for example, there is the description of a light fragment reduction of the same. The reactions taken, for example, crossover the behavior heli-4 and heli-3. This was, we believe this is as confirmation that these mechanisms exist in central nuclear collision for fragment reductions. And however, it is possible only if primary excited cluster, this locally thermalized system, have excitation energy from 6 to 10 MeV per nucleon excitation. This exactly corresponds maximum excitation energy reached in peripheral nuclear collisions for describing fragment reduction from target and projectile nuclear in with the corresponding temperature 6 to which correspond phase coexistence region of the liquid gas type phase transition in nuclear matter. So we can speak about universal mechanism for nuclear reduction, both in peripheral and central heavy ion collision, independently on the way how this matter was produced by thermal expansion, for example, as it is in peripheral collision in the target light, in fragmentation target and light spectator, or in central collisions. This is already just dynamically reduced nucleons. This is concerning statistical details of description. Our system, the main point that at excitation energy more than 10 MeV per nucleon, fragment nuclear matter fragment into locally equilibrized cluster with energy not higher than 10 MeV per nucleon, and final nuclear produced after the decay of such cluster. So this is not directly a coalescence process. This is more complicated process which reduce first excited localized locally equilibrized cluster. And if we apply this idea to the hypernuclear reduction in heavy ion central collision, we will see, for example, that we can reduce a lot of light hypernuclear, for example, in already at 1 GeV per nuclear colliding. And the main point that this hypernuclear reduced in correlation with other particles as the case of locally equilibrized coalescence light clusters. So we have H3 in events, we have reduction hydrogen 3 hypernuclear. We can observe also this kind of correlation. So I'm sorry for this technical problem with my presentation. I finished probably that collision of relativistic ion are very promising process, and we can obtain many high-run system, exotic nuclei with exotic isospin. And the mechanism of this star reduction, this is star range baryon just transported to the spectator residue and captured by nuclear matter. Another mechanism is the nucleation of baryon at subnuclear density. It leads to light cluster and it is affected at all reactivity in central correlation also. In any case, you can read this, and there are big advantages and big future, I guess, for this kind of research. Thank you very much.
Thank you. So, yeah, we had a little accidental session, but if you have questions, we have time for maybe 1 or 2 questions. Any question? No? Participants online, do you have any comments, questions? No? We exhausted the time, actually, for the questions, so we can, if you don't have any questions or comments, we can go ahead and welcome the next speaker. And thanks, Dr. Botvina, for the talk again.
Thank you.
Yeah, so next speaker is Professor Doi, and he's there already? Okay. He will talk about lattice QCD study of hadron interactions with strangeness. So, go ahead.
Okay, I first thank the organizer for this opportunity. So I talk about the QC study of hadron interactions with strangeness. So I want to mention to understand various interesting phenomena in nuclear and astronuclear physics based on the theory, the QCD. So for this purpose, we are aiming at determining hadron forces from first principle QCD calculation. And then we can enjoy the Odyssey from quarks to universe. Now that we are in Renaissance in this field, thanks to the great progress in experiments and observation, and also QCD. And for instance, the impact on neutron star physics has been discussed many times, so I don't repeat. But I just want to emphasize again that we have to know hyperon forces, two-body forces, and three-body forces, to understand neutron star physics and the properties of dense matter. And that QCD can make significant impact. So this is our collaboration, QCD collaboration, people are shown here. So now let me first introduce the theoretical framework. So the studying scattering on the lattice is non-trivial because the lattice in finite volume and smooth states are defined in infinite volume. The first breakthrough was given by Lucius. He considered the wave function and Schrödinger equation at a symmetry region and considered the impact of the boundary condition in finite volume. As this imposes the constraint on energy of the system, then one can derive the continuation condition between energy and the phase shift at that energy. And this relation is called Lucius formula. So what one can do is calculate the finite volume spectrum on the lattice, then convert that information to phase shift via Lucius formula. And this has been a rather traditional approach in QCD. But recently, we developed a new theoretical framework called Hall-Kirsch method. The basic quantity is common to Lucius formula. It is called non-Bethe arbitrary wave function, defined like here. So this is the state and improve the state by hadron operator with separation R, defined like here. And then consider the asymptotic behavior at large R. Actually, the most important property is that one can show that this wave function behavior like here. So the information of the phase shift is encoded, and one can prove it by quantum field theory. But now you see that the behavior is nothing but it's just the same as the usual one in quantum mechanics. So using this fact, we can define and calculate the potential through the equation with the wave function used as inputs. So the potential so defined, of course, the phase to the phase shift by construction. And also one can show that the potential can be constructed in an independent way, although it comes from local in general. And in a practical calculation, we use derivative expansion to treat non-locality. So theoretical formulation is really established for Russell formula and Hurwitz method. But when we consider the multi-hadron or mathematical system of the lattice, we face a challenge. The issue is that there exists an elastic scattering state. So on the volume, spectrum is given like here. So in final volume, it's discretized like here. But essentially, there's a continuum if you go to a larger volume, which means that the energy gap is getting smaller and smaller. And this makes the calculation very difficult because you have to separate these states, for instance, by ground state saturation by taking T to be large enough compared to the energy gap. Then the issue arises, which is so-called signal to noise issue. And there's a spherical formula given like here, where A is a mass number and T is the equivalent time, which should be large enough compared to the inverse of the energy gap. And now I say that the energy gap is getting smaller and smaller, so T should be large, then the signal is ruined exponentially. So in typical number, signal to noise ratio would be as small as 10 to the minus 30 or something like that. And actually, this is essentially similar to the, actually it's another manifestation of sine problem. So how can I do that? How can I do on this session? But people employ the so-called direct method, in which people gave up to take T to be large enough and just take an area T and try to identify a plateau and to determine the energy, and then you use a Russell formula. However, of course, the immediately one would ask that whether this method is really reliable or not, because T is not sufficiently large, so one would expect that excessive contamination could exist. We consider this issue very seriously and developed a completely new theoretical formula, which we call time-dependent Hurwitz method. The point that we use energy-independent potential, which means that we can extract a signal of the potential even from excited state. So this is a master formula, but now with this method, the advantage is very clear, shown in this table. Both direct method, Hurwitz method, can extract a signal from ground state, but for elastic scattering state, direct methods suffer from noise, but we can extract a signal even from these states. In the case of elastic states, excited states, both methods suffer from noises, but it's much easier to be handled because there are some fundamental energy gap between the state of interest and the elastic expression. Which means that in Hurwitz method, we can essentially achieve exponential improvement. And this is a kind of the partial solution of sine problem. And we can go even above elastic threshold by using coupled channel formulas, which is very beneficial to study the hyperloop forces. Now in the committee that we actually make an extensive study for reliability of the elastic shielding method. For that, we and others employed two nucleon systems at heavy quark masses. And there was controversy because with Hurwitz method, we predict the system are bound both spin 0 and 1 channel, although the people who employ direct method claim that the system are bound. So there are clearly inconsistencies. But after our extensive study, we found that the issue is expected contamination in direct method. And after pointed out, people tried to study more, and actually the recent calculation with some improved method called variation calculation show that systems are actually bound. And I hope the next speaker will talk more on this point here. But anyway, now you see that the clear advantage of Harukishi method and the reliability of the method. Now, establishing reliability, now I want to show various results, in particular at point. So we use this Harukishi method with some state-of-the-art hardware at the time, the computer, as well as a new computational algorithm for the core contraction calculation. All three combined, we could perform the first calculation baryon interaction near the physical point. So this is our RSKC setup. It is a 2+1, so UD and S-Cook dynamical flavor simulation. And our pi mass is 146 MeV. So it's very close to the physical point, but slightly heavier than the point. And our volume is as large as 8 Fermi, which is sufficiently large to accommodate two baryons. And we calculate various baryon interaction simultaneously from nucleus sector and hyperon sector for center tensor force in pi-even channel. What is interesting that in experiment, you have a very rich data in nucleus sector, but if there are more strangeness, then it's becoming more difficult. But on lattice, it's opposite. If there are many strange quarks, then you can achieve good signal, and it will be more challenging if you go to the lighter UD quark sector. So we have a strength to make prediction for hyperon forces, and at the middle point, we can make a comparison between experiment and RSKC prediction. So let me show the RSKC result. First, let me give you the bird's eye view. For that, we found that the dynamic potential in SC3 base is very useful. Although calculation is done in fully SC3 taking into account, but we can just look at dynamic potential, which is carries the most information, qualitative information for the potential of an interaction. Here, the octet-octet system, the flavor representation can be decomposed like here. And for 27 plate and 10 bar plate, it's essentially nuclear forces, and you see that the potential resembles spherical potential, reciprocal and active pocket. But then if you go to hyperon sector, it's quite different. For instance, in the middle two, the strong repulsion, and for instance, in the case of the flavor single channel, there is even attractive core. And from these observations, we can understand the physics behind the scene for the short range part. Actually, it turns out the picture based on quark per repulsion and Wang exchange is very good at explaining this behavior. Now, understanding the over bird's eye view, now I want to go more quantitative study. In particular, the attractive core in flavor single channel is interesting because it is related to the HW channel. For that, we study the potential with SC3 being effect fully taken into account explicitly. Namely, we calculate lambda in cascade coupled channel potential. So these are potential, and you see that lambda, there's some attraction, and in cascade, the lion part, and there's strong attraction. And in addition, the photonic potential, you see that it has a non-zero value only at short range, which means that the effect of the cascade lambda coupling is rather suppressed. Now, based on this potential, we can calculate observable, namely the phase shift. So now this figure is for phase shift lambda, and also which is found to be attractive. And also in the cascade, it is strong attraction. And you see that just above the threshold, the phase shift behavior like here. And from this behavior, we found that there is no bound edge diaphragm. However, the remnant edge diaphragm are found to exist. as a essentially the virtual state of in cascade interaction in cascade channel. And this is actually should be also affected from experimental observation. And I hope that some experimental results will come soon at JPAC to confirm our prediction on the fate of its library. Now in experiment, the recent progress for cascade hypernuclei after the experiment, there are several nuclei found, and it seems that there is some SA ground state family here, and also the possibility of excited states like here. And in order for this system to exist, this indicates that in cascade lambda coupling is suppressed. Otherwise, that is cascade hypernuclei will immediately go to the double hypernuclei. So this is a kind of the indirect confirmation about our prediction that in cascade lambda coupling is small. And I expect some more data will come from JPAC in the near future. Now, for the cascade interaction, we can study. So far, I explained about spin 0 channel, but we can determine for all spin 01 channel, spin 01 channel, and these are the results. And dependent channel, one channel is strong attraction, others are weak attraction or weak repulsion. And these features can be brought through the cascade hypernuclei. For that, we study the possible what kind of cascade hypernuclei, light cascade hypernuclei exist with collaboration with Hiyama-san, and we predict that cascade tetrabaryon exists in spin 01 plus channel with very shallow binding energy. And also we are further studying the AGO610 system. For these studies, I just refer to the talk by Hiyama-san. Another comparison explained that femtoscopy is very important way. And this is a comparison between Alice result and our latitude prediction in terms of baryon-baryon collision in heavy ion collision or nucleus-nucleus collision. And you see that you observe a nice agreement. So this shows that latitude prediction is confirmed by experiment. Now we can also study some properties of dense matter, and for that we make some first calculation with some approximation. But however, the results are also interesting. For instance, the right-hand side figure we show the Hyperon single particle potential in symmetrical nuclear matter, and we observe that lambda is strong attraction, cascade weak attraction, assume as repulsion, and these results are rather compatible with experimental information. So this is very encouraging, and this shows that we can make a path from QCD to dense matter physics based on our latitude potential. Now going back to the two-body system, we can predict various interesting divergent channel. For instance, N omega is expected to be a candidate because there is no Pauli principle, Pauli repulsion, and actually potential is found to be universally attractive. And we found that the phase behavior like here, so this shows that this system is bound. Actually, there's an open channel for octet-octet baryon. So this is a quasi-bound state located near unitary limit. And our result is compared with this hematoscopy, and we see good agreement by assuming some another N omega interaction in spin 1 channel. Spin 1 channel. We can also predict the existence of most strange diversion. Actually, this is the potential, and we see that there is strong attraction, and the phase shift behavior like here. And again, we found that the stem is located near unitary limit at di omega, and we expect that the stem can be searched in LHC13. Finally, let me show our very recent result for N5 system interaction. This interaction attract great interest in decades because in relation to the 5-meson mass shift in this matter and also partial chiral restoration. And this is a result for interaction. The potential found to be actually from the one can argue that the long range part should be dominated by 2-pi exchange. And if it is the case, we expect the potential behavior like here. And this is a confirmation. So this is a damping factor plot. And you see that this damping factor getting close to the 2-pi mass if the R is larger than 1 filament. So this is a first observation of the 2-pi exchange in the potential, which is very interesting. Also, based on this potential, we can predict a phase shift. So this attraction to the scatterness is minus 1.4 Fermi or so. And most of the attraction came from the 2-pi exchange tail. And recently, I also show that this attraction, although in this case, the result is a spin average one. So we are now collaborating to extract more information for each interaction. But then this is a very interesting progress to study to determine the N5 interaction. Okay, finally, let me talk about our future prospects. So so far, the results shown obtained near the physical point. Now we are moving on to the physical point simulation. For that, we are using Flux supercomputer, which is recently developed in Japan, which was fastest in the world until very recently, 440 petaflops. And this was developed by co-design of hardware and software, and STC was one of the most important 9 targets. And this is just preliminary status. This is a biomass, scale mass. So previously it was slightly off the physical point. Now our data is exactly on the physical point. So we are now generating information and calculating the hadron interaction.
You should be finishing. Your time is over.
Yeah, okay. And we are also making progress for the analysis. So with the input partial decomposition, we can input a signal from left to right. For instance, even for any lambda interaction can be determined and so on. And another important direction is the 3-body interaction. And this is calculated at very heavy Cope mass, but still we observe the interesting short-range repulsion. And now we are moving, we try to calculate 3-body interaction with hyperon sector in future. So let me just summarize my talk. I don't repeat, just emphasize again that you please expect an interesting result for hadron interaction on the physical point in near future. Thank you very much for your attention.
Okay, thank you. So now it's time for questions. Any questions, comment? Laura Fabietti, there.
Hi, Takumi, is Laura here speaking. I have a question about the lambda NN interaction. So you said you started looking at this. Maybe you can go to the slides. I think you had the slides. Yeah, because you didn't have time to, no, I mean, not lambda N, but the next one, the 3-body.
Oh, 3-body.
Okay, so what is now this R2 that we see here? So what do I see on this plot? Because
Oh, okay. So this is not a lambda N, that's a three nucleon. It's a triton channel. So we, in this case, we fix a geometry of the 3 nucleon and then calculate the interaction between them, and then it subtract the 2-body interaction from which we can determine three nuclear forces, shown in terms of some distance between the center and edge R2.
Okay,
And
I
then
see.
you see that, yeah.
And so the perspective, so or the timeline for Hyperon nucleon, it is of which order? Like 1 year, 2 years, 3 years to have it?
Well, actually, maybe the few years for the simplest one. For hyperinteraction, some channels are easier, other channels are more difficult. Now we are working on the critical generation, so the lambda NN is one of the most difficult part because lambda NN coupled to sigma NN and so on. So therefore, the calculation is more involved. So we are thinking about other like sigma NN, sigma minus neutron, like that as a first calculation for Hyperon three-body interaction.
Okay.
For that, at heavy core mass, I hope we can calculate in a few
Thank
years.
you very much.
Yeah.
Any other question or comment from the audience? No? Okay, maybe I have just a question. It's about the operators. So you have in the source, it's a wall source, right? What kind of operators you have on the sink?
Sink is a point baryon operator. Yeah.
Okay. So you have not tried different kinds of operators for the sink?
For this physical point, we just calculate just a point sink operator. But for heavy quark mass, we ever tried some smearing in the sink. And the reason why we chose a point sink that if we use a smeared sink, then we have a more larger, higher effect from high order in depth expansion. So point sink seem to be best to control the semantic error, and that's why we chose this. For baryon.
Okay.
Yeah.
Just
For
question.
meson baryon, sometimes smeared sink is better. Yeah.
Okay, and just a very quick question. The errors, what kind of errors are including in your results? Is just a statistics, or you have any kind of systematics included?
Okay. Yes. So in this plot, the figure shows the static error, but now you see that the different Euclidean T, the difference give us the estimate about symmetric error originated from net state contamination as well as truncation error in direct expansion. So our final result for this scatterness and so on, I quote both static error and symmetric error.
Only. Okay. Okay, thank you. Any other question, comment? No? Okay, let's thank the speaker again. And
thank you very much.
Welcome Mark Quilla from Washington, the University of Washington. He will talk us about interactions between hyperons and nucleons from lattice QCD. Mark, this will be the time of your talk.
Okay.
Okay,
Thank
you
you.
have to add 5 minutes.
Yeah. Okay. So I want to first thank the organizers for this opportunity. If you know me, I'm Mark Quilla. I'm a postdoc at the University of Washington. And today I will talk about the status of studying nucleons and hyperons with lattice QCD with a direct method. So I don't need to give the introduction here. We all know why we need to understand better the interaction between hyperons and nucleons. And for example, when trying to study neutron stars, spectroscopy, and also medium width decays of hyperons. And these all can be tracked down to the lack of experimental data to constrain this type of interactions. And here, as an example, I'm showing the prediction of the scattering parameters, like the scattering length and the effective range for the cascade nucleon spin triplet state, given by the different potentials, like Megan and Ehime, and also different effective field theory predictions. So we hope that with lattice QCD, we can provide some complementary information about these difficult systems that are very difficult to study experimentally. So lattice QCD is a non-perturbative approach based on the path integral formalism, where we solve QCD on a finite discretized volume. Oh. What happened? Okay, well, here there should be some letters that there are two methods. There's the potential method that Professor Doi presented earlier and the direct method. So here I will focus on the direct method, where finite volume energy levels are extracted from two-point correlation functions. So first, we have to decide what kind of operators we want to use to build these two-point correlation functions. So this is the input, and we have to select them with the correct quantum numbers. Then, from the temporal dependence of these correlators, okay, well, yeah, so when you feed these correlators for the temporal dependence, you can extract the energies of the systems, which should appear here. Okay, something, what is going on? Yeah. Yeah, there's something, there should be a lot of stuff here that is not showing. Yeah.
Anyway, the plots can be seen on the web page.
No, PDF. No, más creo que. No sé si pots connectar el portàtil. Okay, now something's appearing. Okay, yeah. 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 Can you single page view? Okay. Yeah, perfect. Yeah. Yeah, now, yeah, more things are appearing. Yeah, okay.
Okay, you will have 3 more minutes.
3 minutes, yeah. Okay. So, what I was saying, that we have to choose the operators to build these correlator functions. And then from the temporal dependence, we can extract the different energy levels, not only the ground state, but also some excited states. And then we can use, for example, the Lucier method to extract, which gives us a direct relation between the momenta of the system, which can be derived from the energy, to the phase shift, in this case, the cotangent delta. So once we have the phase shift, we can, for example, fit with effective range expansion and extract the different scattering parameters. But also, once we have the scattering parameters, we can also, for example, derive the binding energy. There's an alternative way that we can do this last process, which is going to be talked more in the next talk, which is by using effective field theory to perform this extrapolation to infinite volume of the energies here. And then you can also derive the binding energy. And this method might be better, for example, for larger systems like 3 and 4-body systems where Lucier's methods are more difficult to implement. So once this is a very short summary of the direct method, this is the landscape of the different simulations that the collaborations have performed. I will focus only on the direct approach. So for example, people have used lattice sizes between 2 and 6 Fermis. The lattice spacing, usually people only perform 1 lattice spacing during the calculations, but there are some recent works when they try to compute the discretization effects. I will talk more about it later. And also here I'm plotting the mass of the pion versus, for example, this can be seen as the mass of the strange quark, where some calculations have been performed in the SU3 flavor symmetric limit, but some have tried to fix the strange quark to its physical value and decrease the value of the pion mass, the light quarks. And here are the different systems that people have studied. So since most calculations have performed SVC symmetric calculations, once they study, for example, one system from the 27 era, they study all kinds of different strangeness. So let's start, for example, with the strangeness 0 sector, which is where most of the collaborations have performed calculations. So traditionally, these kind of calculations have been performed using asymmetric correlators, so different operators at the source and at the sink. And this has led to finding these two, for example, these two systems, the nucleon-nucleon spin triplet and spin singlet, to be bound. So at heavier pion masses, they are very bound, and as we decrease the mass of the pion, this binding energy also decreases, as we should expect. People have also studied 3 and 4 body systems, for example, helium-3 and helium-4, and again, they see the same thing. They see that at heavier pion masses, these systems have a larger binding energy. And as we decrease the mass of the pion, this energy decreases. But as we heard in the previous talk, here we have to worry if we are really identifying the ground state of the system or not, or we're just seeing some excited state contamination. Also, we have to be careful if there's an operator dependence on the energies, on these energy levels that we have extracted. So a possible way to answer these questions is to perform a variational analysis. So the first variational analysis was performed in 2019 by the Mainz group, where they studied, the focus of their study was to study the H divarion, but they also look at different IREFs like the 27. And here in this plot, I'm showing the effective mass of using different correlators. So for example, for the green one, they used a type what we call hexaquark operators, which is the product of 6 quarks at the same place. The red points correspond to correlators using divarion operators, so like the product of 2 baryons projected at different momenta. And then the blue point was to perform a variational analysis, but it was not really variational because they had an emission matrix, so you can really see this energy level as an upper bound of some kind of ground state. But nonetheless, they studied this system for the first time with a lot of operators, and what they found is that the 2-nucleon system in the spin singlet state is unbound, so the energy is similar to the energy of 2 free nucleons. The next study was performed by the CALAT collaboration some years later, and in their case, they only included this kind of operator, so like the product of 2 baryons. And what they found that also the 2-nucleon system, the spin singlet, but also the spin triplet, the deuteron, is found to be unbound at this very heavy pion mass. And you can see here by this plot. So this plot is the momentum as a function of the k cotangent delta. And if this system would be bound, the effective range fit should cut this blue line from below, not from above. So they are seeing that this system is not bound at this very heavy pion mass. But in all these calculations, there's something missing. So they are not really including this hexaquark operator in a fully variational way, because we think that this hexaquark operator has a better overlap to a deep bound state compared to the product of 2 baryons projected at different momenta. So the first study that performed this fully variational study was the MPLQC collaboration, where we included not only the hexaquark and divarion operators, but also the quasi-local ones, which are inspired by effective field theory studies, where they know that the wave function of the deuteron decays exponentially with the distance of the 2 nucleons. So we try to mimic this kind of behavior with another type of operator. And this is the spectrum that we observed after performing this study, where we can not only extract the energy for the L equal to 0, the angular momentum 0 system, but also for higher angular momentum, meaning that in principle, we could extract also not only the S-wave scattering parameters, but also the D-wave and even larger partial waves. But the thing here to notice is that we also found that there's in principle an unbound 2-nucleon spin singlet system, and the same for the deuteron. So what is going on here? So what we try to do then is try to see how this spectrum varies as we choose which kind of operators we want to include in the variational analysis. So what we observe is that there's a large interpolating operator dependence in the spectrum. So here, for example, in this plot, what I'm showing is that in the first column is the original spectrum, and in the next columns, we start removing, for example, the operator where there are 2 baryons projected at 0 momenta, and we see that after performing the variational study, we don't observe this energy level. So we see that there are some missing energy levels which are related to the operators that we have removed for the variational basis. So this has already been seen, this kind of behavior, in studying other systems, like for example, the pion-pion system or the nucleon-pion system. And some question that we might ask is that, are we still missing some operators? Because otherwise we should still be seeing consistent energy levels depending if we remove one or two operators. So one question might be that yes, there's a deep bound state, and with the current operators that we have too small of an overlap to this deep bound state, so that's why we are not seeing it. So for example, this is a toy model where we have two operators, A and B, and the operator A has a very small overlap to this deep bound state and a larger overlap to the first excited state. Operator B has a small overlap to the deep bound state and a larger overlap to the second excited state. So when we look at the symmetric correlation functions like AA and BB, they start at the first and second excited state, and after a long time they go down to the ground state as expected. But when we look at the asymmetrical correlator, this correlator goes directly to the deep bound state, which is what we have seen in all the previous studies. However, when we put these two operators in a variational analysis, what we see is that the ground state and first excited state of the matrix for small times still couples to the first and second excited state. And we have to wait very long times until we see that these operators really follow the ground state and first excited state. So that's one of the reasons why we are not seeing still this deep bound state. Another reason is that there's really no deep bound state. There are some things that we still have to answer because we don't really have answers. So for example, we see that for all our energies that we extract, there's a volume independence for the ground state. So if one expects that the ground state that we are extracting has contaminations from excited states, in principle, these excited states really depend on the volume that you are computing. So if we see that the ground state is the same on the different volumes that we compute them, there has to be some kind of really special cancellation within the excited states and ground states to produce this volume-independent ground state. Also, we perform on the phase shifts that we extract and the scattering parameters, all the checks and seeing that the parameters that we extract make physical sense. There's also consistency, for example, when studying the scalar matrix elements of light nuclei, if we compute them in a direct way of these scalar matrix elements or an indirect way, and we see that they give the similar values. Also, when studying, for example, the general baryon-baryon interaction, we observe this SU6 symmetry, which has been predicted by the large NC limit. There's also calculations of magnetic moments and these cross-sections that agree with experimental values, etc. So there are a lot of things that have to be answered if what we're really extracting are not the ground states. There's also these other studies where people have used lattice QCD data to match effective field theories. For example, here in this work, they fix the two antibody coupling constants to the energies of the two nucleon systems on helium-3, then check that for the helium-4, they get some similar value compared to the lattice data, and then predicted the larger nuclei. And this has been extended up to oxygen and calcium. So these kinds of studies might be possible to extend to hypernuclei, for example, when we have the lambda nucleon and lambda nucleon forces, and predict also hypernuclei directly from lattice QCD. And lastly, there's another option where we see these discrepancies is because they are coming from lattice spacing effects. So up till 2018, there were two kinds of calculations on the HD baryon system, where there was one with the direct method by the MPL-QCD collaboration, the purple points, and also by the HAL-QCD method, the blue points. And there was some discrepancy at very heavy pion masses. Then, in 2018, came the mains group, which performed the first variational calculation on two baryon systems, where here, to get these points, they only included the baryon-like operators. And later on in 2018, they performed the first extrapolation to the continuum for two baryon systems. And what they observed is that there's a large dependency of the binding energy as a function of the spacing. So they computed values between a spacing of 0.1 Fermi up to 0.4 Fermis. And they see that there's almost like 30 MeV difference between the coarsest lattice and the finest one. So these discrepancies between the different collaborations might be due to using different lattice spacings. But then also we have, for example, to consider like this point by the MPLQCD collaboration computed here used a lattice spacing of 0.123 Fermis, which according to this calculation should be well above 40 or 50 MeV. So these calculations really depend on what type of gauge fields are you using, and they should be corroborated by other collaborations if they see also these effects on the lattice spacing effects. So as a summary, here I have shown you that we can use lattice QCD to reach systems that are very difficult for experimentalists, like the strange systems, and it's still not clear what are the best operators to include in a variation analysis for two baryons. So we are having an ongoing study where we include additional operators and also a study an extra volume at this very heavy pion mass to really understand what is really going on. And we are also starting production for different baryon-baryon channels at very close to the physical point around a pion mass of 170 MeV with different volumes. But beyond all this spectroscopy, we are also interested in matrix elements, which are very important for current experiments. For example, studying the momentum fraction of light nuclei, matrix elements for beta decay and double beta decay, both neutrinoless and neutrinoful, also scalar and tensor matrix elements, and other things. So, thank you very much.
Actually, you are ahead of time. I mean, you had 3 more minutes and didn't add it.
2 minutes minus
okay.
5.
5. Okay. Is there any question in the audience or comment regarding what Mark presented? Laura?
Very nice talk, thank you. I have a question about the scattering parameters for pi or mpi, because I mean, if I understood correctly, you show like the energy spectrum, right?
No, I didn't show the spectrum for the. What I said was that they find similar things, that they have to include a lot of operators to see that the energy spectrum doesn't depend on what type of operators they include.
But do you have any prediction for the scattering parameters for pi or npi?
We haven't performed any calculations for pi or mpi yet.
But can you do that?
Principally, yes.
I mean, because you have baryon only, right? I see. And in baryon, I mean, can you go back to your slides number? This one. Okay, yes. So basically, okay. So this is for lambda, right?
Yeah.
Yeah. Okay. And so, if you now change baryon species, is, let's say, the precision of your calculation independent from the quark content, or changes very much?
Yeah, the more strange quarks we have in the system, since they are heavier, they have a better signal-to-noise ratio. You can extract the better precision for your value. So the more stranger the system is, the better you can extract.
So it would be great to have a calculation from you, by you, for example, nucleon omega that we have measured. And if you extract scattering parameter, one can maybe compare to the data we have now. Would be really great.
Yeah, I mean, we will have to perform the calculation at the physical point, which which is difficult because there's a nucleon involved. But yeah, in principle, there's no reason to not do it. Yeah.
Thank you very much.
Yeah, thank you.
Another question there, Nirparea?
Thank you for the nice talk, but I am, at the end of it, a bit confused. I'm looking at this graph, for example, and which number should I take home?
Sorry?
Which number should I take home?
Depending on the, so now it's not clear which values to take, for example, at these unphysical pion masses, because the 3 different collaborations obtain 3 different values. So things still have to be cleared out before we can really say, okay, at this pion mass, there's this binding energy. So at the moment, it's not clear.
Okay, thank you.
Yeah.
Any other question? A comment? No? Okay, so let's thank Mark again. And well, we have Bazak, Professor Bazak, talking about pionless effective field theory in flavor SF3.
Okay. Can I show my presentation? Okay, it works. So good afternoon. I would like to say a bit about pionless effective field theory and the flavor reduced symmetric limit. Actually, it's closely connected to the last presentation of the NPL-QCD of Mark, because it's based actually on their results. And as Nir just commented, it's based on their old results. So let's hope this holds. Okay, so let's start. So we would like to construct an effective field theory, why it's needed, why it's helpful, because typically in physics we have some underlying theory which its mass scale is much higher than the physics that one would like to inspect. So if you are about low energy physics, you don't have a resolution to find the fine details of the potential, for example, and therefore it's not needed to include all of this physics into your calculation. For example, if you would like to calculate nuclear structure, you do not have to solve a QCD, of course, because of the different mass scales between them. So effective field theory is the framework to systematically do this, go from the underlying theory, integrate out the not needed degrees of freedom, and the details of the underlying theory is encoded in the lex of your theory. So for example, if you are deal with a physics that even the mass of the pion is considered as a high energy physics, so you cannot see the resolution of the PAM. So the one pion exchange potential, for example, can be seen as a contact potential. And if you know how to construct a series that takes into account more and more details about the calculation, if you know how to order this series, so you can construct some theory that is a systematic expansion of the underlying theory. So this is the idea about pionless effective field theory in principle, and pionless effective field theory is actually the simplest of them. So consider you have, I don't know, so two spinless particles. So at leading order, you need just one operator, which is a contact. Now this is, in the momentum space, it's just a constant. In the coordinate space, it will be some delta function. And if you go another order, you just would like to find the first correction due to momentum. So you would get something like that. And if it's an unnatural case, what we call it means close to unitarity, we have shallow bound states. So you need to iterate the leading order to all terms, therefore equivalent to solve the Schrödinger equation. But if you would like to continue to NLO, you cannot do that because of the Wigner bound. So you should take into account the NLO as a perturbation in a perturbation theory. So this is very, very simple. I think the simplest theory that one could imagine. But this is not as simple as that, because when one goes to the three-body system and try to calculate with the mechanism that I just described, the energy of the three-body system, he sees, or one sees that it just depends on the cutoff that he had to implement to the delta function, because of course it's too singular to calculate. And therefore, because this cutoff is not physical, any observable cannot depends on this cutoff, and this Thomas collapse actually, the fact that the energy goes to minus infinity is something unphysical, and one needs to introduce a three-body force at leading order, and this was known for some years now. And actually, this is just a manifestation of the Efimov physics that exist in such a system, in a bosonic system or in nuclear system. So you have a discrete scale invariance, you have infinite number of bound states, you have such a Borromean binding when the two-body system is not bound and the three-body is bound. So this is, of course, well known. And surprisingly, we found a few years ago that if one goes to NLO, one needs to add a four-body force. And therefore now this is taken from this recent review of Hammer, Sebastian, and Birel and Gok. And now we trying to, or starting to understand the power counting in parallelist effective field theory, and this is how it's look like. So we have 2 nucleons, 3 nucleons, 4 nucleons at leading order and L. So, okay, I just have a beautiful introduction about lattice QCD, so I need to say nothing, and I skip also that. But then, if one can calculate some binding energy within lattice QCD calculation, it still needs to extrapolate its results. So we just, Mark just told us about extrapolation to zero spacing between the lattice sizes, but there are 2 other extrapolations to be taken. One is to take from a finite box to infinity, to the continuum. And the other one is that, okay, you can calculate results for 2, 3, 4, I don't know, 5 baryons, but this, of course, cannot go like that to heavy nuclei or even medium nuclei. So one needs to know somehow how to extrapolate, how to bridge the gap between lattice QCD results and real nuclear or hypernuclear physics. So I won't tell anything about this issue, but let's focus on how to get the results out of the box. So of course, the famous tool here is Lucia formula. In the 80s, it just calculated a model-free way of how to take into account the effect of the box. So if one knows that, and he has some calculation of some lattice sizes, of course, it can extrapolate to infinite L, and therefore get the results after the box. But okay, this holds for the 2-body system. What if one would like to have for heavier system, I don't know, 3, 4, or 5? So there is a lot of work about that. I would just mention one work, which is the work of Sebastian Koenig and Dean Lee, which says that if one deals with a system that the closest breakup is into 2 subclusters, I don't know, consider helium-6 that is now broken into deuteron plus, okay, whatever, yeah, 4 plus 2 subcluster, which are bound, and if one can consider this subcluster as a point-like particle, so, okay, Lucia formula just holds. So there is some complication of combinatorial factors and something like that, but then the relevant momentum should be the relative momentum between these subclusters. The relative mass should be the reduced mass of this subcluster, and then, okay, you can just use Lucia formula. So we would like to check how this works and if it can be used in lattice QCD extrapolation. So our first comment is that Lucia formula is a asymptotic formula, and one needs to be very careful when he would like to use it to real extrapolation of data, because, okay, look at it. This is what you did here is just to assume that parallelist CFT is the ultimate, the nature itself, and therefore use lattice QCD, parallelist CFT in order to calculate, okay, so this parallelist CFT was fitted to real nuclei, to the deuteron, triton, binding energy, and the scattering length. And therefore, we calculated using some version of stochastic variation method in a box. We calculate the binding energy inside the box of this 3 system, 2, 3, and 4 nucleons. And now just, plot it as a function of the delta beats, the difference in the energy between the free space and the box, and multiply by the box size L as a function of L. So Lucia just said it should be exponential, and indeed it is. Yeah, here the free space parameters was calculated. This is a plot with no fitting parameter. So we need to know the binding energy, and we need to know the ANC, the asymptotic normalization coefficient, which both calculated outside of the box, and then we just no fitting parameter and see, okay, Lucia formula works perfect. But, okay, look at the lattice size. This is extra a very, very big lattices, boxes. So of course, one cannot do calculation with a 60 Fermi box. Well, so we need to zoom in into the regime which is relevant to lattice QCD calculation. For example, I don't know, up to 10 Fermi or something like that. So this is the zoom in that you have there. And one can see that indeed there is a very big deviation between Lucia formula, which is an asymptotic formula, and the real results. And this is a logarithmic scale, so this is real big differences. Okay, so let's do it, try to be more quantitative. How large the box should be in order that we can get an accurate result from extrapolating box results using Lucia formula. So the left plot is for the binding energy, and we take 3 boxes. For example, the point in 10 uses boxes with 8, 10, and 12 Fermis, and then using just a Lucia formula to calculate or to extrapolate the binding energy and the ANC. And one can see that, okay, if the boxes are 2, 4, 6, you get, very not accurate results. But around 8, 10, it starts to stabilize, and one can get a good result. So this is a hint to the lattice QCD guys. This is the regime that one can work in order to get a good extrapolation. And the right plot is for the ANC. ANC is more tricky to calculate because it's, in the Lucia formula, it's the prefactor of the exponent, so it's very sensitive to the details. And now one can see that you have, the regular Lucia formula, it's the first order correction, but we have some other exponentially suppressed correction to the Lucia formula, like we show here. So the first one is the well-known, but the other one is just to sum next to next neighbors to your lattice and the one other. So one can see that going from the red one, which is the Lucia formula of only the first correction, the leading order correction, going to the next shell, the situation improves quite significantly. So it's of course good to do that. But even though this is just works in the asymptotic regime, okay, so you can, with the leading order Lucia, you can, I don't know, if you would like to have a really accurate result for the NC, one need to go to, I don't know, 40 Fermi. So with that, with the next correction, it can be done with 25 Fermi or something like that. But of course, these are quite large boxes. So this is the numbers that we got from this approach. But the alternative approach that Marx also mentioned is just to construct an effective field theory, which, if it can be solved, and it can be solved directly on the lattice, on a box, with a periodic boundary condition, one can fit its parameters directly from the box calculations, and therefore the extrapolation can be done with this effective field theory. So this is an approach that we introduced several years ago, and this is the results for the nuclear case. So as I mentioned, a Pauli CFT at leading order has only 3 parameters, so 2 channels of the 2-body channels and 1 3-body potential. So one need just 3 points. Okay, we have much more than that, of course, in LPLQCD 2013 results, and therefore we can fit everything. We don't need actual helium-4, so helium-4 is a prediction or post-diction because they calculated it. And of course it goes, like Mark showed, it goes very nicely with the NPL-QCD result. So this is for real nuclei, for regular nuclei, but I promised to say something about SU3. So what happens if you would like to expand this study to the whole hypernuclei regime? So we know, of course, that the flavor SU3 symmetry is one of the main building blocks of all the quark theory. And if one would like to go to see what's happened to the 2 baryon, so we need to take into account the Clare-Jordan series of 2-octet baryons. So again, Mark showed that you won't get 6 EREPs. Actually, we saw it twice today. So, but if one assume, or if one would like to study the ground state, and if one assume that this ground state is, the spatial part is symmetric to permutation of particles, we know that the flavor spin wave function should be antisymmetric, and therefore we know how to couple the spin EREPs and the flavor EREPs in order to get a total antisymmetric wave function, like it's done in this NPL-QCD calculation. And therefore we know what is the state that we would like to calculate. We still need to construct the Hamiltonian, or the Lagrangian, if it's a Pi-less FT. So we would like to write the Lagrangian, which is, of course, consistent with the SU3 cross SU2 symmetries. And the idea here is to use the Casimir operators. And the identity, we know that in the SU2, there is a single Casimir plus the identity. And in SU3, we have 2 Casimir operator, and again, identity in this subspace. So multiply that, we get 6 operator, which is just like other approaches which uses traces of the baryon tensors got. So like this paper by Savage and Weiser. But take into account this specific situation that the cubic operator of SU3 is its eigenvalue is 0 for all symmetric EREPs. And therefore, if one can just play around and see that there is some linear dependence between this operator, and just only 5 parameters need to be calibrated. So we use NPL-QCD, that calculation of for the SU3 flavor symmetry point. So they calculate several 2-body, 3-body, 4-body system in this plot. So for the 2 baryon system, if we know how to decompose the SU2 and SU3 EREPs, and we know how to combine them to construct antisymmetric state, we can just take the results, which is the dots, the results calculated by NPL-QCD for all EREPs, and then just extrapolate them to infinity, and then do also the lambda. It's this is not the hypernuclear lambda. This is a small lambda, which is the cutoff, the cutoff of this Pi-less FT. And therefore, to see that everything is converged quite well. And the interesting point here, that if we assume that just the Casimirs are the operators that enter to our Pi-less effective field theory, the 8S EREP, which cannot be resolved in NPL-QCD calculation due to the operator that they take there, can be a prediction of this theory. So this is our result. 3-body stats, similar situation, of course, more complicated spin and flavor EREPs, but due to the fact that in the spin part, one does not have the totally antisymmetric state, so the symmetric states in the flavor are not physical, and one can construct just the combination of flavor and symmetry and spin EREPs that gives the right symmetry. We can get only 14 physically allowed EREPs. So in this approach, one needs 14 data points in the 3-body sector in order to actually finish the whole effective field theory at this order, and therefore all the rest, 3, 4, 5, whatever, by the calculation will be a prediction. Unfortunately, NPL-QCD gave us just 4. So we can use these 4, we can extrapolate them to infinity, out of the box. We can see how it goes with lambda, but we cannot do predictions for other states because there is not enough data to fix all the legs. Just to mention that the other approach, which use traces of baryon tensors, has 18 operators of three-body state, so this approach is more economical. And my last slide, for 4 baryon systems, it's even more complicated, so the symmetry consideration becomes a bit cumbersome, but of course can be done, it's just, bookkeeping. But up to now, we just did the simplest one, which is 28 bar, equivalent to helium-4, so actually these results are equivalent to what I showed you in the nuclear case, and but I would like to note that the fact that one see that this quite large difference when the cutoff is changing between, I don't know, 2 inverse Fermi to 20 inverse Fermis says that the NLO correction here, or hints toward the conclusion that NLO corrections here will not be negligible, and one needs to do that. So I will leave you just with the conclusion. Just would like to thank my collaborations, which their names are just here, and specifically to 2 which sit here, which our excellent postdoc fellow Martin and Nirmania. Thank you.
Thank you very much for this nice talk. So, are there any questions? Evgeny Appelbaum.
Yeah, thank you very much. Interesting talk, beautiful results. If you maybe can go back to the slide where you show the advantage of the extrapolation to the infinite volume using pineless EFT in comparison with the Lucia formula.
Well, we did not compare it directly.
Yeah,
if
okay.
you consider that one.
Okay, so I'm curious, what is actually the dynamics that is incorporated in pineless EFT and is missing in the Lucia approach that helps you to make extrapolation more efficient? Because both of them are based essentially on the principles like analyticity and so on and so forth. There is essentially no dynamical input. So I'm curious which ingredient allows you to be more efficient at the Lucia approach when doing these extrapolations.
So this is not a comparison between the pineless way of extracting to the Lucia, because pineless was considered as real results, just to see how Lucia is against that. So this is not a fair comparison, which we are now working on that. But I think that if one look at that thing, so one can see that the next to leading order Lucia correction works well, but just in the asymptotic regime. So one needs a completely different correction in the regime, which is, I don't know, 10, 15 Fermi's box. So I don't think that some small correction to Lucia formula, some exponentially suppressed term that we just missed could help us. So this, I think, because of the mix of the scales here. So the scale of the neutron is not so small that you can say, okay, that you have a real separation of scales of the potential range, wave function range, box, which is Lucia assumption.
Any other question or comment from the audience here? Yeah, is she here?
Thank you for a nice talk. And would you please go to page 13? You used the NPL QCD result and fit the pineless EFT to guess the final result, continuing result. And what happens when you use the Carolat result or Mainz result, Carolat and the other one? Anyway. Those also uses the direct method and obtained the energy for a finite box. Then the results should be the same for the same pion mass and same. Anyway, in the continuum limit, then in the free space, then we should see the same result for the same pion mass. And did you try using the Carolat result and Mainz result for this extrapolation with the pionless EFT?
No, we just did it with MPL-QCD. Of course, it can be done. It's just, brings of concept.
If the free space extrapolated results are different, then the energy itself measured in the lattice QCD at finite volume is something is different and some contradiction exists. Is that the conclusion which you can draw from this extrapolation?
Well, there are two kinds of extrapolation here. One is to extrapolate between finite lattices to infinite lattice.
Yes.
Where this extrapolation is not really needed here, because you see that the points that you have at the very right size of the plot is the plot of is actually the extrapolation done by lattice QCD, where they just assume that the largest box that they have is the infinite volume, which is not bad if your lattice, if your box size is about 7 Fermis, and if you are dealing with unphysical masses, so everything is very compact. So at that case, this is not a bad approximation. Therefore, this is what they do. The other extrapolation here is the extrapolation from the 2 and 3 body stuff to the 4 body, which it's not needed here because they calculate it directly, but it's just to say, okay, with that data, we can now calculate, the other or heavier nuclei, and therefore it's important.
Thank you very much.
Just one more question or comment? No? Okay. Then, thank you very much for this nice presentation. Thanks to all the speakers of the session today, and now we have the poster session, right? Probably an announcement.
So now we will have poster session, which will start, of course, with refreshment. Hopefully it's outside. So take your refreshment. Then there are supposed to be posters, and authors of the posters are supposed to be close to their nearby, discussing with you your questions and comments. Then we have 3 online video presentations, 4 minutes long, of Ibuki Terashima about analysis of coupled channel potentials with quark and hadron degrees of freedom, then Ebata Kengo about preparation status of missing mass spectroscopy for cascade hypernuclei, and then Fio-Miat Lin analysis of energy uncertainties generated from density of emulsion layer and range straggling. So the online presentation will be broadcasted. These 3 videos will be broadcasted in about 10 minutes, let's say at 4:15. Each will take 4 minutes, and then you can follow this on the screen, there or over there. And then after these online presentations, you can ask the authors. You may have questions like as we have online presentations or our presentations. So now please, we are starting poster session. If you have some comments, I expect you that you will stand up and go eat and drink. And you are still sitting, I am confused. Then the poster session finishes at 5 o'clock, and I suggest you to really finish at 5 because it takes some time to get downtown to the public lecture. It's about, I would say, 30 minutes from here.
like to thank everyone for coming today. My name is Pumia Lin, and I'm a third year.
So, may I have your attention, please? So we will start the sequence of these three posters, which are given by video, and we will be starting with Pio Miat Lin talking about analysis of energy uncertainty generated from density of emulsion layer and range straggling.
Hello, I would like to thank everyone for coming today. My name is Pumia Lin, and I am a third-year doctoral student from Gifu University, Japan. Today I would like to give you a short introduction of my research, and the title of my presentation is Analysis of Energy Uncertainties Generated from Density of Immersion Layer and Range Struggling. The purpose of this presentation is to share with you my findings regarding with mass error of double Happen nucleus. Firstly, I would like to introduce you our experiment, JPARC EU7 experiment. The main purpose of this experiment is to investigate the characteristic of bion-bion interaction by creating double lambda Happen nucleus in the nuclear emulsion. Like this kind of event we can see in the nuclear emulsion. And currently, 33 events of double lambda Happen nucleus were detected from the first period of emulsion analysis. The interaction in double lambda Happen nucleus can be understood by measuring the mass of double lambda Happen nucleus. In the case of Niagara event, the mass of lambda HEC can be understood by measuring the mass and kinetic energy of decay total particles, lambda HE5, proton, and pi minus by using range energy relation. In the range energy relation, measurement of density of immersion layer at beam exposure time is very important because the density and the thickness of immersion layer were changed after photographic development. As you may know, the alpha tech from Polion 2 and 2 of Thorium series were used to calibrate the shrinkage factor and the emulsion density. However, the relation between emulsion density error and mass measurement error was not sufficiently steady. So my study is to find the sufficient number of attacks for the calibration to minimize mass error of double lambda Happen nucleus. In my research, the sufficient number of attacks was determined using the relation between kinetic energy and kinetic energy error. In this, kinetic energy error is generated from the density error with number of attack dependence. Then I can determine the sufficient number of attack by using kinetic energy error. In my result, at least 150 alpha is enough to utilize for the density calibration. Moreover, the range struggling is counted as a statistical error in the analysis of double Happen nuclei. Therefore, kinetic energy error from range struggling was also calculated to be 1 order of magnitude larger than that of density error, as shown in this figure. This is the summary of my presentation. The sufficient number of objects was determined to be at least 150 alpha, and the kinetic energy error from range struggling was calculated to be 1 order of magnitude larger than that of density error. Based on my result, I believe that it is now possible to provide minimizing mass error of double lambda Happen nucleus in the future analysis. Thank you for your attention. If you are interested in my research, please visit to the poster session. My contribution ID is 85.
Okay. So now we can jump directly to the second poster, which will be preparation status. Yes, question? So are there any questions? Does not seem to be the case, so we can proceed to the second poster, which is preparation status of missing mass spectroscopy for Xi hypernuclei with S2S magnetic spectrometer. So,
hello everyone, my name is Ken Uebata from Kyoto University and JAEA in Japan. I will talk about the preparation status of missing mass spectroscopy for Xi hypernuclei with S2S magnetic spectrometer. This picture was taken from downstream of K1.8 beamline in JPARC last week. At K1.8 beamline in Hadron Hall of JPARC, The missing mass spectroscopic experiment for xyhypernuclei called JPAG E70 experiment is in preparation now. In this experiment, high-intensity and high-purity K- meson beam with 1.8 GeV over C momenta is used to produce xyhypernuclei via the K- K+ reaction in carbon-12 target. The beamline spectrometer composed of QQD/QQ magnets measures momenta of K-. And the newly installed S2S magnetic spectrometer composed of QQD magnets measures K+ momenta with the resolution 6.0 times 10⁻⁴ power. By using these detectors, the resolution of missing mass is aimed at less than 2 MeV to discriminate each energy peaks of xyhypernuclei. However, the particle passing through S2S magnets are not only K+, but also proton and pion as background events. To suppress these background events, 3 PID counters, TOF, L-Cherenkov counters, and Volta-Cherenkov counters are placed at the downstream of S2S magnets. As preparation status, the research and development of detectors were already done. Currently, the frame of active fiber target as carbon-12 target is designing now, and the frame of the upstream MWDCs in S2S called SDC1 and 2 is designing now. The S2S magnets and the downstream MWDCs called SDC3, 4, and 5 were installed. The PID counters, TOF, L-Cherenkov, and Volta-Cherenkov counters will be installed 2 weeks later at the downstream of SDC5. On December in 2022, the preparation will be ready. From January in 2023, the beam time will begin. In summary, at K1.8 beamline in JPAG, the missing mass spectroscopic experiment for xyhypernuclei is in preparation. The S2S magnet and downstream MWDCs were already installed at K1.8 beamline. The preparations to install the PID counters and upstream detectors after July is in progress currently. Thank you.
Okay, so again, we have some space for questions. Are there any questions? So this 2 MeV looks quite challenging. So how are you going to, let's say, so what is the main ingredient of this for this resolution? Hello, do you hear me? Okay, so we will go to the next one. So this is a analysis of coupled channel potentials with quark and hadron degrees of freedom by Ibuki Terashima. We cannot hear him. Thank you very much. So are there any questions? I do not see anybody. Okay, so thanks once again, and this is it.